From the moment human beings first tilted their heads toward the night sky, light has been the faithful courier of secrets. Every star, every planet, every distant cloud of dust and gas sends forth streams of light that journey across unimaginable distances to reach us. Our eyes were the first detectors, crude but wondrous, able to translate these faint beams into meaning. Yet, as astronomy matured, light revealed itself to be more than just a thing we could see. It became the universal messenger, carrying within it the fingerprints of matter, motion, and temperature. The universe is silent in sound, but radiant in light. It is through this radiance that we piece together the story of worlds far beyond our reach. To study planets that orbit other stars, astronomers must rely on the delicate relationship between matter and light. Every planet reflects some of the light from its parent star, just as Earth reflects the glow of the Sunday. How much light is reflected is not random, but a precise physical property known as albedo. Albedo describes the fraction of incoming light that a surface or atmosphere sends back outward. A world covered in ice has a high albedo, because ice bounces most light away. A world shrouded in dark oceans or carbon-rich rock has a low albedo, because most light is absorbed rather than reflected. This measurement is more than a simple number. It is a window into composition, climate, and atmosphere. By studying brightness, astronomers can deduce whether a planet has clouds, oceans, deserts, or something stranger still. The act of measuring this brightness is delicate. Stars blaze with overwhelming brilliance, while their planets are tiny companions, reflecting only a small fraction of that energy. To detect this faint echo, astronomers use the most powerful tools at their disposal. Telescopes gather the light and focus it, while sensitive detectors count every photon that arrives. Photometry, the science of measuring light intensity, allows researchers to notice when a star dims ever so slightly as a planet crosses in front of it. Spectroscopy, which separates light into its rainbow of colors, goes further, revealing the presence of atoms and molecules in a planet's atmosphere. These tools transform light from a simple glow into a language that can be read. Through them, astronomers are not just gazing, they are interrogating the universe, asking questions and receiving answers encoded in photons. Brightness alone does not tell the whole story. Reflection matters equally. The way light scatters from a planet depends on the size and composition of the particles it encounters. A cloud made of water droplets will scatter light differently than a cloud made of methane crystals or silicate dust. On Earth, we know this well. Snowfields gleam, oceans shimmer, forests absorb. Each surface has its own relationship with light, and from space, Earth's average reflectivity stands at about 30%. That figure is not arbitrary. It is the result of water clouds, polar ice, desert sands, and ocean basins, all working together. By comparing Earth's albedo with those of Venus or Mars, we understand how atmosphere and surface shape a world's identity. Venus, wrapped in thick clouds of sulfuric acid, reflects more than 70% of the sunlight it receives, appearing dazzlingly bright in our skies. Mars, with its dusty surface and thin atmosphere, reflects much less. These comparisons give context when astronomers examine exoplanets, for they show the range of possibilities within our own solar system. The challenge of studying albedo across interstellar distances is immense. The planets are invisible pinpricks next to their parent stars, drowned in radiance. Yet clever techniques allow us to separate the faint planetary signal from the overwhelming glare. Phase curves, for example, track how a planet's brightness changes as it orbits its star, much like watching the phases of our moon. When the planet shows its day side toward us, we catch the maximum reflection. When the night side faces us, the brightness drops. From these subtle variations, astronomers extract an albedo value, turning minute changes in light into profound knowledge. As telescopes improved, so too did our ability to read these whispers of light. Instruments in space, freed from the turbulence of Earth's atmosphere, provided unprecedented clarity. The Kepler spacecraft revolutionized the field by continuously watching over 150,000 stars, detecting tiny fluctuations in brightness that revealed planets in orbit. The Transiting Exoplanet Survey Satellite, or TESS, expanded this work across nearly the whole sky. These missions transformed speculation into certainty. The universe proved to be teeming with planets, each one reflecting and absorbing light in its own way. This mastery of light is not just a technical achievement, but a philosophical one. It reminds us that knowledge does not always require direct touch. We do not need to land on a distant planet to know something real about it. By studying how it interacts with starlight, we can measure its size, orbit, atmosphere, and sometimes even its weather. Light becomes both map and message, drawing boundaries around the unknown. And yet, as powerful as these methods are, they occasionally reveal results that challenge expectation. For in the expanding catalogue of planets, some worlds appear ordinary at first glance, but then surprise us with properties that defy intuition. Among them are worlds so dark that they reflect less light than coal, less even than the blackest asphalt. These planets absorb nearly everything their star shines upon them, glowing only faintly in the dim red heat they emit back into space. To find such a world required every skill astronomers had developed. To understand it required confronting the limits of atmospheric physics. And so the study of light leads us, paradoxically, into darkness. To study planets is to study how they interact with light. And sometimes, what they show us is the near absence of reflection itself. The story of light is also the story of human ingenuity, for each step in astronomy has been marked by the quest to measure dimmer, fainter, and subtler forms of radiance. Centuries ago, astronomers relied only on their eyes and simple lenses to gather the glow of stars. With patience, they recorded positions, mapped constellations, and tracked the wandering planets that drifted slowly across the heavens. They did not yet know the physics of light, but they trusted that these beams carried truth. When Isaac Newton showed that sunlight could be split into a spectrum of colors, a new world of meaning opened. Suddenly, light was not just brightness but structure, a pattern that could be analyzed. Later, Joseph Fraunhofer identified dark lines within that spectrum, signatures of atoms absorbing precise wavelengths. This discovery meant that by reading the spectrum of light from a distant object, one could deduce its chemistry without ever touching it. In that moment, astronomy became not just geometry, but physics and chemistry played out on the grandest scale imaginable. The leap from stars to planets was enormous, for stars burn with their own brilliance, while planets are small bodies that only reflect borrowed light. To see a planet around another star is to search for a candle flickering beside a floodlight. Yet persistence, mathematics, and technology combined to make it possible. By the late 20th century, astronomers had refined instruments sensitive enough to detect minute changes in starlight as a planet passed in front. This method, called the transit method, became the most powerful means of exoplanet discovery. Each transit is a tiny eclipse, a dip in brightness that repeats with perfect rhythm. From its depth, astronomers measure the planet's size. From its timing, they measure its orbit. And by examining the slight difference in brightness when the planet passes behind the star, they estimate how much light the planet was reflecting. Thus, the albedo of distant worlds emerges not from a photograph, but from the subtle mathematics of light curves. The principle of albedo connects the familiar with the alien. On Earth, albedo governs climate. White clouds and ice sheets keep our planet cooler by reflecting sunlight, while dark oceans and forests absorb heat. When ice retreats, albedo drops, and more sunlight is absorbed, creating feedback that accelerates warming. This is not abstract physics but lived reality, measured by satellites and felt in weather patterns. By studying Earth in this way, scientists gain insight into exoplanets. A hot Jupiter close to its star, if it has reflective clouds, will shine more brightly in visible light than one stripped bare by heat. Conversely, a planet with an atmosphere rich in dark, light-absorbing molecules will appear nearly invisible beside its star. These principles, tested at home, give meaning to the data we gather from afar. One might imagine that brightness is easy to measure, but the universe is rarely so kind. Stars, flare, and pulse. Detectors have noise, and photons arrive in random fashion. Astronomers must sift through these imperfections with rigorous statistical methods. They build models of stellar variability, subtract instrumental errors, and repeat observations to confirm faint signals. Only then can they claim that a tiny drop in starlight corresponds to a transiting planet. When the signal is repeated hundreds of times, the confidence grows, and the albedo measurement gains weight. The discipline is cautious by necessity, for false positives lurk in every dataset. But when the evidence holds, the reward is profound. Out of the glare of a star emerges the identity of a hidden world. The contrast between star and planet is not only immense in brightness, but also in scale. A planet like Jupiter is more than 10 times smaller in diameter than the Sun, and it reflects a fraction of the sunlight that falls on it. At interstellar distances, this faint reflection is like spotting a firefly beside a lighthouse. To overcome such odds, astronomers design instruments that push the boundaries of sensitivity. Space telescopes operate above Earth's atmosphere, avoiding the distortion of air. Detectors, cooled to near absolute zero, reduce thermal noise. Algorithms sharpen signals by combining multiple transits into coherent curves. It is a triumph of both engineering and patience, for sometimes years of observation are needed to build a reliable portrait of one planet's brightness. These methods transform the field of planetary science. Where once we knew only the handful of worlds orbiting our own sun, now we recognize thousands orbiting other stars. Each discovery expands the diversity of what a planet can be. Some are gas giants, so close to their stars that their atmospheres boil. Others are rocky planets, locked in eternal daylight or darkness. A few orbit dim red stars, receiving just enough warmth to host liquid water. Within this diversity, the measure of albedo becomes one of the most telling clues. It is not enough to know that a planet exists. To understand it, we must know what it does with the light that touches it. Light is not only a scientific messenger, but also a poetic one. Consider the journey of a single photon that leaves the surface of a star hundreds of light years away. It travels across space for centuries, never wavering, until it strikes the cloud tops or atmosphere of a planet. If reflected, it continues its voyage, escaping the pull of that world and traveling onward until it finally enters the lens of a telescope orbiting Earth. Inside the detector, its energy is converted into an electronic signal, recorded in a database, and eventually analyzed by human minds. From that tiny event, conclusions are drawn about the composition and nature of an entire planet. The scale of inference is staggering. From one particle of light, we build worlds. And yet, this reliance on light also reveals its limits. Not every photon tells us what we wish to know. The brightest signals can overwhelm the faintest. The path through interstellar dust can scatter and dim, and some molecules absorb light at wavelengths beyond our instruments. To overcome these challenges, astronomers must continue building ever more precise telescopes. They must expand observations into infrared and ultraviolet, each carrying different messages about temperature and chemistry. They must combine data from multiple instruments to paint a fuller picture. Every improvement in sensitivity peels away another layer of ignorance, bringing us closer to understanding planets as they truly are. The deeper truth is that light has always been central to our survival as a species. We learn to track seasons by the position of the sun, to navigate by the stars, and to measure time by shadows. The scientific revolution did not invent this reliance, it extended it. Now, in the age of exoplanets, we once again depend on light, but with tools far beyond naked eyes or sundials. Light is not just a guide, but a dataset, a reservoir of information waiting to be unlocked. With every planet measured, the language grows richer. With every unexpected result, the universe pushes us to refine our models. Thus, the study of light is a journey into both knowledge and humility. For even as we learn how to decode its signals, we also learn how fragile our assumptions can be. Some worlds reflect more than we expect, others far less. Some atmospheres shimmer with clouds, others swallow light whole. Each deviation from expectation is a reminder that planets are not designed to fit our predictions. They are what they are, and it is up to us to interpret the story their light tells. And that story will soon carry us to a discovery so strange that it seems almost to resist illumination itself. The more we study the heavens through the language of light, the more we recognize that the universe is both familiar and alien at once. A beam of light obeys the same physics, whether it strikes the surface of a lake on Earth or a cloud top on a planet orbiting a distant star. The same principles of reflection, absorption, and scattering apply everywhere. Yet the results differ wildly depending on the conditions of each world. On Earth, the play between oceans, continents, and atmosphere sets a balance that maintains life. On Venus, the choking shroud of carbon dioxide and sulfuric acid clouds produces a mirror-like brilliance, reflecting so much sunlight that it dazzles our skies even while the surface below broils at more than 400 degrees Celsius. On Mercury, lacking a thick atmosphere, the surface is dark and scarred, reflecting less than 1/3 of incoming sunlight. The diversity of albedos within our own solar system is already striking. To extend that diversity outward, across the galaxy, is to encounter a realm of possibilities so broad that it strains imagination. To capture these faint whispers of brightness, astronomers treat light as both subject and tool. They record how it shifts, how it fades, how it brightens again. In the smallest dip of a star's light, they see the passing silhouette of a planet. In the faintest glow beside a star, they detect the scattering of starlight by alien clouds. The task demands both precision and patience. Telescopes must stare for months or years at the same stars, building records of light curves that reveal the rhythm of orbits. Each curve is like a heartbeat, steady and repeating, announcing the presence of a world that cannot otherwise be seen. From these patterns emerge deeper insights. If a planet reflects strongly, its curve will show brightness increasing as it moves into a phase where more of its day side is visible. If a planet reflects weakly, the curve will flatten, signaling an absorber rather than a mirror. Some planets glow brightly in the infrared, re-radiating the energy they have absorbed as heat. By combining visible light measurements with infrared observations, scientists can separate reflection from emission, uncovering the balance of energy that defines a planet's climate. This balance tells us not just what a planet looks like, but how it lives under the gaze of its star. Consider the contrast between Earth and Jupiter. Earth reflects roughly 1/3 of the sunlight that strikes it, balancing between reflective clouds and dark oceans. Jupiter, a gas giant, reflects about half, its atmosphere filled with ammonia clouds that scatter light. To an observer far away, Jupiter would appear brighter than Earth, though its surface is hidden beneath thousands of kilometers of gas. This teaches us that brightness does not necessarily reveal habitability or surface conditions. It reveals only the interaction of light with the outermost layers of a world. Understanding this nuance is critical when applying albedo measurements to exoplanets. The methods used to measure albedo in distant systems are triumphs of subtlety. One technique relies on secondary eclipses, the moment when a planet passes behind its star. When the planet is visible, the combined light of star plus planet reaches the telescope. When the planet slips behind, only starlight remains. The difference between these two measurements, often only a fraction of a percent, reveals how much light the planet was contributing. From this difference, astronomers derive the albedo. Another technique uses phase variations, watching the gradual change in brightness as the planet moves from new to full, mirroring the cycle of our moon. These shifts, mapped carefully, build a picture of reflectivity across an entire orbit. The reliability of these methods is strengthened by repetition. A single eclipse may be uncertain, blurred by noise or stellar activity, but dozens or hundreds of eclipses, aligned and averaged, produce a clear signal. Over time, patterns emerge that no random error could explain. This is the patient art of astronomy, transforming faint flickers into solid science. Each photon recorded is a vote cast for one interpretation of reality. Collect enough votes, and the truth emerges from the tally. In this way, albedo becomes more than a number. It becomes a story. A high albedo suggests clouds or ice. A low albedo suggests haze or absorbing gases. When paired with spectral data, These measurements can hint at specific molecules: water vapor, methane, sodium, potassium, titanium oxide, all leave their marks in the spectrum of reflected light. The deeper we look, the more we can say about the invisible. It is as if light itself were a code, and astronomy, the discipline that slowly learns the cipher. But this story also holds surprises. Not all planets fall neatly into the categories we expect. Some are brighter than their temperatures should allow, while others are darker than any natural surface on Earth. These anomalies are not errors but discoveries. They show us that planetary physics, when pushed to extremes, can yield results outside our familiar range. Clouds may fail to form under intense heat. Exotic molecules may absorb wavelengths of light unfamiliar to our laboratories. Worlds may exist that swallow almost everything their star offers, leaving them cloaked in near total darkness. Thus, the journey that begins with understanding light leads us inevitably to its absence. To know what reflection means, we must confront what happens when reflection disappears. This is not just a technical puzzle, but a philosophical one, challenging our sense of what a planet should be. For if light is the universe's most reliable messenger, what are we to make of a world that refuses to send light back? It is here, at the edge of visibility, that the story of one of the strangest discoveries in modern astronomy begins. A planet so dark that it reflects less light than coal. A planet that absorbs almost everything that falls upon it. A planet that stretches the very definition of what we thought possible. This world is called TRES 2b, and it will carry us deeper into the mysteries of darkness than we have ever gone before. For most of human history, the idea of planets beyond our own solar system lived only in speculation. Ancient philosophers wondered whether other worlds might exist, circling distant stars, perhaps even hosting life. Yet such musings remained philosophy, unprovable and beyond reach. For centuries, the night sky offered no evidence that stars were anything more than luminous points. Even when telescopes revealed the moons of Jupiter or the rings of Saturn, the question of other planetary systems remained unanswered. The stars seemed fixed, silent, and solitary. To imagine them as suns surrounded by worlds was an act of faith rather than science. That began to change in the 20th century, when technology advanced far enough to let astronomers measure the tiniest shifts in starlight. They realized that a planet, though invisible, could betray its presence through the effect it had on its parent star. Gravity links the two together, causing the star to wobble ever so slightly as the planet circles around it. This wobble, measured as a subtle change in the star's light, offered the first real path toward detection. Even then, success was elusive. Instruments lacked the sensitivity, and claims of discovery often fell apart under scrutiny. For decades, the search was filled with false starts, leading many to doubt whether detection was possible at all. The breakthrough came in 1995, when Michel Mayor and Didier Queloz announced the discovery of a planet orbiting the star 51 Pegasi. This planet, later called 51 Pegasi b, was a gas giant about half the mass of Jupiter, circling its star every 4 days. The method of discovery relied on radial velocity, the precise measurement of the star's spectral lines as they shifted back and forth due to the planet's tug. This announcement shook the astronomical community. Not only had a planet around another sun-like star been found, but it was nothing like what theorists had predicted. Instead of a distant giant like Jupiter, it was a blisteringly hot world hugging its star in a close orbit. The discovery proved two things at once. First, exoplanets were real and detectable. Second, the architecture of planetary systems was far more varied than the solar system had led us to expect. This opened the floodgates. With improved spectrographs mounted on powerful telescopes, more planets were soon detected. Dozens became hundreds, each new one adding to the growing catalogue. Some were hot Jupiters, like 51 Pegasi b, others smaller, orbiting farther out. Still, the limits of ground-based observations meant progress was slow. Astronomers longed for a dedicated mission in space, free from atmospheric interference, to watch the stars continuously and with unmatched precision. That mission arrived in 2009 with the launch of Kepler. Positioned far from Earth, the Kepler spacecraft stared at a single patch of sky, containing over 150,000 stars. Its task was simple yet revolutionary. It would record the brightness of each star with exquisite accuracy, waiting for the telltale dimming caused by a planet crossing in front. This transit method offered a direct way to measure planetary size, something radial velocity alone could not provide. Within months, Kepler began delivering candidates. Within years, it had confirmed thousands. The picture of the galaxy changed forever. Planets were not rare. They were common, almost inevitable. The Milky Way was revealed to be a galaxy of worlds. Among Kepler's discoveries were rocky planets only slightly larger than Earth, orbiting within the habitable zones of their stars, where liquid water might exist. Others were giant planets with orbits shorter than a single Earth day. There were systems with multiple planets packed tightly together, systems with planets circling faint red dwarfs, systems that defied every prior expectation. The sheer diversity was staggering. Suddenly, the question was not whether planets existed, but how many types there could be. The success of Kepler inspired further missions. The Transiting Exoplanet Survey Satellite, or TESS, launched in 2018, expanded the search to nearly the entire sky. Instead of focusing deeply on one region, TESS scanned widely, identifying planets around bright stars, close enough for follow-up studies. This made it possible not only to detect planets, but also to study their atmospheres using instruments like the Hubble Space Telescope and, more recently, the James Webb Space Telescope. The field of exoplanet science matured rapidly, moving from discovery to characterization. With thousands of confirmed planets now catalogued, astronomers began to look for patterns. They asked how planetary size and orbit related to the properties of their stars. They studied the frequency of Earth-sized planets in habitable zones, the occurrence of gas giants, the prevalence of planets around red dwarfs. The statistics suggested that nearly every star in the galaxy hosts at least one planet. Many stars host several. The implication was profound. Planets are not rare jewels, but fundamental outcomes of star formation. Yet within this explosion of discovery, anomalies emerged. Some planets reflected far less light than expected. Some had atmospheres so puffed up, they nearly touched their stars. Others were dense as iron or light as styrofoam. Each deviation from the familiar solar system reminded astronomers that nature is more inventive than theory. And among these anomalies, one stood out. A planet so dark that it seemed to swallow nearly all the light that struck it. A planet whose existence challenged assumptions about reflectivity and clouds. A planet that became the darkest ever measured. From ancient speculation to modern detection, the rise of exoplanet science set the stage for this extraordinary finding. It showed us that the universe is filled with worlds stranger than fiction, each one a laboratory for physics on scales Earth could never provide. And in this vast catalogue, hidden among thousands of entries, lies a planet that reflects less light than coal. The next step in our story is to understand how we measure such darkness and what it means for our picture of the cosmos. The growth of exoplanet science after the discovery of 51 Pegasi b was not a steady march but a surge of breakthroughs, each one building on the last. The radial velocity method, which had first revealed the hot Jupiter orbiting 51 Pegasi, remained central in the early years. Astronomers refined their spectrographs, designing instruments that could detect stellar wobbles as small as a few meters per second. This precision was enough to reveal planets smaller than Neptune, orbiting stars hundreds of light years away. Each new detection proved that Mare and Quilos had opened a genuine door into the hidden architecture of the galaxy. Even so, radial velocity had limitations. It measured only the tug of a planet on its star, which meant the true mass of the planet remained uncertain unless the orbital tilt was known. If the orbit was edge-on, the signal matched the planet's real mass. If the orbit was inclined, the planet could be much more massive than the measurement suggested. This uncertainty left astronomers hungry for a complementary method, one that could break the ambiguity. That need was fulfilled by the transit method. The transit method worked not by watching the star wobble, but by recording its brightness as a planet crossed in front. Every time the planet passed, the star dimmed by a tiny fraction, often less than 1%. By measuring the depth and duration of this dip, astronomers could calculate the size of the planet and its orbital period. When radial velocity and transit data were combined, the results were powerful. Size plus mass yielded density, and density revealed composition. A world could be identified as rocky, gaseous, or somewhere in between. For the first time, exoplanets became more than points on a chart. They became physical objects with measurable properties. The impact of the Kepler spacecraft was transformative because it harnessed the transit method on a scale never attempted before. Kepler did not glance briefly at stars but fixed its gaze on one patch of sky for years, measuring their brightness with relentless accuracy. The result was a flood of discoveries, not just of individual planets, but of entire systems. Some stars hosted 5 or 6 planets, each orbiting in tight, harmonious chains. Others revealed planets slightly larger than Earth, the so-called super-Earths, which had no counterpart in our own solar system. Kepler showed that planetary systems are diverse and common, a revelation that reshaped astrophysics. The data also revealed statistical truths that would have been invisible without such a survey. One was that small planets are far more common than large ones. Another was that hot Jupiters, while dramatic, are relatively rare. Perhaps most tantalizing was the finding that a significant fraction of stars host planets in or near their habitable zones, where liquid water could exist. These statistics provided not only scientific insight but also a sense of perspective. For every world like Jupiter or Earth, there may be dozens of others orbiting distant suns, waiting for us to detect their faint signatures. The flood of discoveries demanded new ways to organize and analyze information. Catalogs swelled with thousands of entries, each containing orbital periods, radii, and estimated masses. Teams of scientists built models of planetary system formation, trying to explain the sheer diversity. Why did some systems pack planets close to their stars, while others stretched them far apart? Why did some planets form as giants while others remained small? These questions kept theory and observation in constant dialogue. Every new dataset from Kepler or TESS was a chance to refine the models or challenge them. While space telescopes were essential, ground-based observatories still played a vital role. Networks of robotic telescopes scanned the skies for transits, confirming candidates and refining orbital details. Instruments like the high-accuracy radial velocity planet searcher, known as HARPS, delivered the precision needed to weigh small planets. Together, the global community of astronomers built an ecosystem of discovery, each facility contributing a piece of the puzzle. As methods matured, the focus shifted from simple detection to characterization. If a planet passed in front of its star, some of the starlight filtered through its atmosphere before reaching us. By examining the spectrum of this light, astronomers could infer the presence of molecules like water vapor, methane, or carbon dioxide. This technique, called transmission spectroscopy, transformed exoplanet science yet again. Planets became not just dots in catalogs, but atmospheric laboratories, with chemistry that could be studied across light years of space. Yet even as these tools advanced, some planets resisted easy explanation. A few reflected far less light than expected, their albedos hovering near zero. They absorbed nearly everything their stars offered, glowing faintly only in the infrared. Such worlds challenged assumptions. If Jupiter could reflect half of the sunlight it received, why did some of its cousins reflect almost none? If Venus could blaze with brightness thanks to thick clouds, why did other gas giants lack reflective coverings? These puzzles hinted at atmospheric processes unfamiliar on Earth, processes that could only be glimpsed through careful measurement of light. The rise of exoplanet science was therefore not just a story of detection, but of humility. Each discovery revealed more diversity, more complexity, and more ways in which the solar system was not a universal blueprint, but one example among countless variations. Planets came in unexpected sizes, surprising orbits, and astonishing levels of brightness or darkness. The catalogue grew not into a list of familiar worlds, but into a library of strangeness. And in that library, one entry stood apart as perhaps the most unusual of all, a planet discovered not because of its brilliance, but because of its near-total absence of reflection. That world, later known as TRES 2b, would force astronomers to reconsider what it meant for a planet to interact with light. Its discovery was not an accident, but the culmination of decades of work, an inevitable outcome of the tools and methods honed since the first wobble of 51 Pegasi b. The stage was set, the methods perfected, and the universe ready to reveal one of its darkest secrets. The success of Kepler and the rise of exoplanet catalogues transformed astronomy from a search into a census. Where once a single discovery was headline news, now dozens arrived each month. The sheer abundance of planets shifted the central question. Instead of asking whether other worlds exist, astronomers began asking what kinds of worlds dominate the galaxy, how they form, and why they differ from one another. The discipline matured from exploration into comparative science, with the goal of understanding populations rather than individuals. Yet within that population, certain planets stood out, not because they were typical, but because they were extreme. Some of these extremes revealed themselves through size. There were planets larger than Jupiter, but with masses so low that they resembled bloated balloons, their atmospheres puffed up by heat from their stars. Others were dense as iron, suggesting strange histories of violent collisions that stripped them of lighter material. Some orbited so close to their stars that a year lasted only a few hours, their daysides scorched by relentless radiation. Others drifted far from their stars, orbiting once in centuries, frozen and remote. These discoveries taught astronomers that the familiar arrangement of the solar system was not a universal template, but a local accident. Planets came in every form the physics of matter allowed, and sometimes in forms that stretched theory to the breaking point. Among the most surprising discoveries was the existence of hot Jupiters. These massive gas giants, orbiting extremely close to their stars, had no equivalent in the solar system. Their very presence was a puzzle, for planetary formation theories suggested giants should form far from their stars, where icy materials are abundant. To explain hot Jupiters, scientists proposed migration, a process where planets form at greater distances and then drift inward due to gravitational interactions with the surrounding disk or with other planets. These ideas reshaped our understanding of planetary system evolution. The hot Jupiter, once an anomaly, became a key laboratory for testing models of formation and migration. But anomalies were not limited to size or orbit. Some planets surprised by their brightness, others by their darkness. Albedo, the measure of reflectivity, became a critical tool for separating expectation from reality. Jupiter's clouds make it relatively bright, Venus even more so. Yet some exoplanets revealed albedos lower than any major body in our solar system. They reflected less light than asphalt, less than charcoal, absorbing nearly everything their stars poured onto them. These worlds challenged the assumption that clouds were a universal feature of gas giants. If clouds failed to form, or if exotic molecules filled the atmosphere, the result could be a planet shrouded in darkness. The ability to measure such dim worlds depended on relentless advances in photometry and spectroscopy. Phase curve analysis, which tracked the variation of brightness as a planet orbited its star, became central. By watching how the combined light of star and planet shifted with orbital phase, astronomers could tease out the faint reflection from the overwhelming stellar glare. It was a triumph of subtlety, turning tiny differences in light into planetary portraits. Yet the more planets were measured, the clearer it became that darkness was not rare. Instead, it was a recurring theme, one that needed explanation. Public fascination followed these discoveries with enthusiasm. Headlines spoke of scorching worlds, diamond planets, and rogue wanderers adrift in interstellar space. The idea that the universe contained such diversity captured the imagination far beyond the scientific community. When a planet was reported to be darker than coal, the story resonated deeply. Darkness, after all, carries metaphorical weight as well as physical meaning. To call a planet pitch black was to invite awe, to conjure images of a world unlike any we had known. Within the scientific community, the implications were no less profound. Measuring the albedo of planets meant probing their atmospheric physics in ways that theory alone could not predict. Each low albedo planet provided data about temperatures, pressures, and chemical compositions in regimes beyond earthly experience. They showed that planetary science was not only about finding analogues to Earth, but about exploring the full parameter space of what planets can be. Darkness was not a defect, but a clue, a signpost pointing toward processes yet to be fully understood. As the catalogue expanded, so too did the need for classification. Scientists began grouping planets not just by size and orbit, but by reflectivity, density, and atmospheric behavior. Patterns began to emerge, though many remained tentative. Some hot Jupiters formed clouds of silicates or aluminum oxide that reflected light, making them bright. Others, subject to higher temperatures, remained cloudless and absorbed almost everything. The diversity was staggering, but the extremes defined the boundaries of possibility. By the end of the second decade of the 21st century, exoplanet science had matured into a discipline with its own specialties, its own debates, and its own tools for resolving them. Observatories across the world and satellites in orbit worked together, each contributing data to the ever-growing archive. Machine learning algorithms combed through the immense datasets, identifying transit signals invisible to the human eye. Meanwhile, theory raced to keep up, refining models of planetary atmospheres to explain both the bright and the dark. All of this set the stage for a discovery that would redefine what darkness meant in astronomy. Out of the countless planets catalogued, one emerged as the darkest ever found. It was a hot Jupiter orbiting a star much like the Sun, discovered not by accident, but by the careful work of a survey designed to search for transits. When its albedo was measured, astronomers were astonished. Less than 1% of the light striking it was reflected. It was darker than coal, darker than asphalt, darker than any known natural surface on Earth. This planet was named TRES 2b. Its discovery was not only a landmark in the catalogue of exoplanets, but a moment that forced scientists to reconsider how light interacts with matter under extreme conditions. In the rise of exoplanet science, it stood as a milestone, a case study of the unexpected. The story of light as a messenger now turned toward the study of near-total darkness and the physics that made it possible. When astronomers speak of darkness in a scientific sense, they do not mean mystery or fear. They mean reflectivity, the cold arithmetic of how much light a body returns to space after starlight falls upon it. The measure is called albedo, and it is one of the simplest yet most powerful numbers in planetary science. Albedo is expressed as a fraction between 0 and 1. A perfectly reflective surface, like an ideal mirror, has an albedo of 1, meaning it reflects all the incoming light. A perfectly absorbing surface has an albedo of 0, swallowing every photon that touches it. No real surface reaches these extremes, but the concept provides a scale upon which all planets can be measured. On Earth, satellites have mapped our planet's albedo with precision. The average value is about 0.3, or 30%, meaning roughly a third of the sunlight that reaches Earth is reflected back into space. This average conceals a dynamic interplay. Bright clouds reflect much more, dark oceans reflect much less. Ice caps glisten with high reflectivity, while forests absorb sunlight efficiently. Seasonal changes alter the balance, and long-term climate change shifts it further still. From this one number, scientists can infer much about Earth's climate system, its feedback loops, and its sensitivity to solar input. Other planets in the solar system reveal their identities through albedo as well. Venus, with its thick, permanent clouds of sulfuric acid, has an albedo of about 0.75. It gleams in our skies as the evening star, outshining every celestial object except the Sun and the Moon. Mars, dusty and dry, reflects less than Earth, its reddish surface absorbing more light. Jupiter and Saturn, cloaked in ammonia clouds, hover near 50% reflectivity. Uranus and Neptune, with methane-rich atmospheres, are similar. Even Mercury, though close to the Sun, is dark, reflecting only about 10% of the light that strikes it. Each world's albedo is a fingerprint of its atmosphere and surface, a key that unlocks deeper understanding. To compare planetary albedos to everyday materials helps anchor the concept in experience. Snowfields on Earth approach values near 80 or 90%, reflecting almost everything. Desert sand reflects perhaps 30 to 40%. Oceans reflect only a small fraction when the sun is high, absorbing nearly all the incoming energy. Asphalt, charcoal, and coal, some of the darkest natural surfaces, reflect less than 10%. To imagine a planet darker than coal is to imagine a body that seems to swallow starlight whole. The difficulty is that exoplanets are far too distant for direct comparison. They cannot be measured with a handheld radiometer or photographed with surface detail. Their albedos must be inferred from light curves, secondary eclipses, and spectral analysis. The science is indirect, yet no less reliable when performed with care. A planet transiting its star provides the first clue. The depth of the transit reveals size, while the brightness before and after reveals whether the planet adds any reflected light. If the difference is vanishingly small, the albedo is low. If the difference is marked, the albedo is higher. Repeated measurements across multiple orbits build confidence, and combining visible light with infrared further separates reflection from emission. Even with these methods, uncertainties remain. Stars are not perfect lighthouses. They flicker and flare. Their surfaces seethe with convection and magnetism, creating brightness variations of their own. Instruments are never flawless, and detectors record noise alongside signal. The challenge is to disentangle these complications, to isolate the planetary contribution from all the rest. This requires statistical rigor, long-time baselines, and independent confirmation from different instruments. Only then can astronomers declare with confidence that a planet is truly as dark or as bright as it appears. Despite these challenges, the measurements have been made, and they have revealed surprises. Some planets, expected to have high albedos due to possible cloud cover, turned out to be dim. Others, thought to be scorched and bare, reflected more than expected. The diversity was striking, but among it, one result stood apart. A hot Jupiter discovered in the constellation Draco, orbiting a star similar to the Sun, showed an albedo of less than 1%. This meant it reflected less light than black acrylic paint, less even than the blackest asphalt. It was by far the darkest planet ever measured. The implications of such a number are staggering. How could a planet the size of Jupiter, orbiting so close to its star that it blazed with heat, fail to reflect almost anything at all? What atmospheric processes could strip it of clouds or fill it with absorbing gases strong enough to swallow nearly every photon? These questions pushed theory into new territory. For if albedo is the signature of a planet's outer layers, then a planet with near zero albedo is telling us that something exotic lies in its skies. To measure planetary darkness, therefore, is not simply to assign a number. It is to probe the chemistry, temperature, and dynamics of alien atmospheres. It is to test the limits of what molecules can survive under extreme radiation. It is to compare the laboratory physics of light absorption with the vast, uncontrolled experiments conducted by nature in the furnaces of hot Jupiters. Each new measurement is not just a statistic, it is an invitation to rethink the possible. And so, from the simple concept of albedo, astronomers reach toward profound insights. By studying how much light a world reflects, they learn about what it is made of, how it formed, and how it behaves under the relentless glare of its star. Darkness, once a metaphor, becomes a measurable property, a clue written in photons. With these methods, scientists were ready to confront one of the strangest worlds yet discovered, a planet darker than coal, darker than asphalt, a giant world that seemed determined to remain invisible. Its name was TRES 2b, and its discovery would mark a turning point in the story of planetary light. To understand what it means for a planet to be dark, one must first return to the laboratory of our own solar system. Here we have the advantage of proximity, the ability to send spacecraft and landers to record albedo, not as a distant signal, but as direct measurement. Earth's reflectivity, hovering near 30%, is not uniform. The glint of sunlight off oceans, known as sunglint, can momentarily raise local reflectivity. Polar ice caps increase it in winter, while cloud cover changes daily. Volcanoes add particles that brighten the skies temporarily, while deforestation and melting ice reduce reflectivity over decades. Albedo is therefore not only a property of surface or atmosphere, but also a living indicator of change. Venus offers the opposite extreme. Its dense clouds reflect 3/4 of the sunlight they receive, making it dazzling to telescopes and human eyes alike. Yet beneath this brightness lies a surface of hellish heat, proving that reflectivity alone does not dictate climate. Mars, with its iron-rich dust, reflects little, its albedo around 15%, creating a planet of muted brightness. Each world teaches a lesson. Venus proves that bright worlds can be inhospitable, while Mars shows that darker worlds can be barren and cold. Together, they remind us that albedo is a clue, not a full diagnosis. The gas giants provide further examples. Jupiter, massive and majestic, reflects about half the sunlight it receives, thanks to its high, bright clouds. Its bands and zones, visible even through small telescopes, are not just patterns, but albedo differences written large. Saturn too reflects strongly, though its rings complicate the measure, adding dazzling brightness beyond the planet itself. Uranus and Neptune, with atmospheres rich in methane, reflect similarly. These values form the baseline expectations when astronomers turn their eyes outward. If our gas giants are bright, it seemed natural to expect others to be as well. When the first hot Jupiters were found, astronomers anticipated that clouds would form in their upper atmospheres, scattering light and giving them albedos similar to Jupiter or Saturn. Instead, the measurements revealed something far darker. This was startling because it suggested that high temperatures near the star prevented cloud formation, leaving atmospheres dominated by molecules that absorbed light instead of reflecting it. Sodium, potassium, titanium oxide, and other absorbers could exist in gaseous form at thousands of degrees, creating skies that swallowed photons like ink. The process of measuring such effects from afar relies on careful subtraction. Imagine a planet orbiting a star. When the planet is beside the star, both star and planet light combine. When the planet passes behind the star, its contribution disappears. The difference between these two moments reveals the planet's brightness. If the difference is vanishingly small, the planet reflects almost nothing. This method, called secondary eclipse photometry, is one of the most direct ways of measuring albedo in exoplanets. It requires exquisite precision because the signal is often only a few parts per million. Yet with space-based telescopes, such measurements are possible, and they have revolutionized our understanding. Complementing this method are phase curves. As a planet orbits its star, the amount of its illuminated side visible to us changes, just as our moon waxes and wanes. By tracking the system's brightness over time, astronomers reconstruct how much light the planet contributes at different phases. A bright planet shows a strong variation, peaking when the day side is fully visible. A dark planet shows little variation, its curve almost flat. Phase curves not only reveal albedo, but can also hint at heat distribution, winds, and atmospheric circulation. They are maps of worlds we cannot resolve, drawn only from light. These tools make exoplanet albedo one of the most challenging but rewarding measurements in astronomy. They allow us to compare distant giants to our local ones, to test whether the rules of reflection hold across light years. They also force us to confront surprises. When an albedo comes back near zero, the finding cannot be dismissed. It must be explained. It must be tested against models of chemistry and temperature, against laboratory data on absorption, against everything we think we know about planetary skies. In this sense, measuring planetary darkness is less about tallying numbers than about confronting limits. What molecules survive at 2000 degrees Celsius? How do aerosols form or fail to form under such radiation? How does pressure change scattering? Every unusually dark world becomes an experiment set by nature, a puzzle waiting for theory to catch up. By the late 2010s, enough data had been gathered to suggest that darkness itself might be common among hot Jupiters. Not all were pitch black. but many were far darker than expected. This forced a shift in theory. Perhaps high temperatures stripped away reflective condensates. Perhaps unusual molecules filled their skies. Perhaps energy transport within their atmospheres suppressed cloud formation entirely. Each possibility revealed more complexity, and each discovery added urgency to refined models. It was within this framework that one world, TRES 2b, stood out. Its albedo was not just low, it was nearly zero. Less than 1% of starlight was reflected, making it darker than the darkest coal. The planet became a benchmark, a reminder that the cosmos can produce outcomes far outside the familiar. By studying how darkness manifests in its skies, astronomers hope to learn not just about one planet but about the rules governing many. Thus, the measurement of planetary darkness is not the end of the story but its beginning. It shows us that light, the universal messenger, can sometimes return with a message of almost complete silence. It challenges our models, forces new experiments, and reminds us that even the simplest measurement, a fraction of reflected light, can open doors to deep questions about chemistry, physics, and the diversity of worlds. The pursuit of planetary albedo across light years is not just an exercise in numbers. It is a confrontation with the fundamental ways that matter and radiation interact under extreme conditions. When astronomers declare that a planet reflects less than 1% of the light that strikes it, they are not describing a casual observation. They are summarizing years of measurement, calibration, and theory, compressed into a single startling conclusion. Darkness, in this sense, is not a void but a phenomenon, one that reveals the workings of atmospheres more exotic than anything on Earth. Consider the chain of reasoning behind such a measurement. A telescope records the brightness of a star over time. Within that record lies a barely perceptible rhythm as a planet transits and orbits. Astronomers subtract noise from the data, model the star's variability, and align hundreds of transits. They search for the moment when the planet passes behind the star, expecting to see a tiny dip as its reflected light vanishes. If the dip is absent, or nearly so, the albedo is close to zero. This is the logic of secondary eclipse detection. It does not rely on guesswork. It relies on repetition, statistics, and the stubborn persistence of signal emerging from noise. To ensure accuracy, multiple instruments must confirm the finding. A single telescope could be fooled by instrumental quirks, but when different observatories produce the same result, confidence grows. Hubble's optical detectors, Spitzer's infrared sensors, and ground-based photometers together provide complementary views. Each measures slightly different wavelengths, teasing apart reflected light from emitted heat. When all point to the same conclusion, that the planet contributes almost no visible reflection, the case for extreme darkness is secure. What could cause such a phenomenon? The physics of light offers several pathways. At high temperatures, reflective clouds cannot form, leaving the atmosphere bare. Instead of bright ammonia or water clouds, the skies are filled with molecules like gaseous sodium and potassium, which absorb strongly in the visible spectrum. Titanium oxide and vanadium oxide, if present in gaseous form, absorb even more efficiently. These molecules transform the atmosphere into a sponge for photons, letting little escape. The result is a planet that appears almost invisible beside its star, glowing faintly only in the infrared where it radiates heat back into space. On Earth, we know the experience of walking on asphalt on a hot summer day. The surface absorbs nearly all sunlight, becoming painfully hot to the touch. Now imagine a planet the size of Jupiter, coated not in asphalt, but in an atmosphere filled with absorbers far more efficient. The heat is not local but global, the absorption not shallow but thousands of kilometers deep. Such a planet is not just dark, it is transformed into a thermal reservoir, trapping and re-radiating energy in ways that challenge our climate models. Yet even in such darkness, subtle details may emerge. A small fraction of light could still be scattered by molecules high in the atmosphere, or reflected from deep clouds, revealed only in certain wavelengths. Phase curve studies sometimes detect brightness shifts that hint at winds carrying heat from one side of the planet to the other. The night side, though hidden, can still emit infrared radiation, revealing circulation patterns. Thus, even when a planet seems to swallow visible light, it still whispers information in other parts of the spectrum. Darkness is never absolute. It is a selective silence. The importance of these measurements extends beyond curiosity. By studying extremes, scientists refine the boundaries of theory. If a planet can reflect less than 1% of light, then any model of planetary atmospheres must account for such cases. Laboratory experiments on light absorption by hot gases gain new urgency, for they provide the data needed to interpret observations. Computational models of circulation and chemistry are tested against reality. Each dark planet, though difficult to study, becomes a benchmark against which theory is judged. In the end, measuring planetary darkness reveals as much about us as about the planets themselves. It shows how far we are willing to go to extract meaning from faint light. It shows the ingenuity required to transform noise into knowledge, photons into physics, and it shows the humility of science. For every time we think we know what a planet should look like, the universe produces a counterexample. Brightness is not guaranteed, clouds are not universal, and some worlds will simply refuse to shine. The story of albedo in exoplanets therefore leads us to a paradox. By studying light, we encounter the absence of light. By chasing brightness, we discover darkness. And within that darkness lies one of the most remarkable planets ever found, a world darker than coal, orbiting so close to its star that it should blaze with reflection, yet sending back almost nothing. This planet, TRES 2b, would become a symbol of the unexpected, a case study in the limits of planetary physics, and the next step in our journey into the extremes of the cosmos. The path to discovering one of the strangest planets known began not with a mighty space telescope, but with a network of small robotic observatories on Earth. In the early 2000s, before Kepler transformed the field, astronomers were already experimenting with ways to find exoplanets using relatively modest equipment. One such effort was the Transatlantic Exoplanet Survey, or TRES, a collaboration between observatories in the United States and the Canary Islands. The strategy was simple but powerful. Instead of building a single enormous telescope, the team deployed several smaller ones, each designed to monitor wide patches of the sky for the telltale dimming caused by planetary transits. These telescopes, though only about 10 centimeters in diameter, were equipped with sensitive detectors and precise clocks. Their small size allowed them to watch large fields of stars at once, trading depth for breadth. It was a method well suited to the hunt for giant planets orbiting close to their stars, where transits would be frequent and relatively easy to spot. In 2006, the survey targeted a star in the constellation Draco, catalogued as GSC 03549-01845, later identified more precisely as a G-type star, similar to our Sun. For weeks, the telescopes recorded its brightness, accumulating a steady stream of data points. Amid the noise and variability that always accompany ground-based observations, the astronomers noticed a recurring pattern. Every 2.5 days, the star dimmed by about 1.5%. The dip was shallow but regular, repeating with clock-like precision. This was the signature of a planet, large enough to block a noticeable fraction of starlight, orbiting extremely close to its star. Follow-up observations confirmed the signal. Radial velocity measurements showed the star wobbling in harmony with the transit timing, the tug of a massive planet pulling it back and forth. The mass was consistent with a gas giant, and the size, inferred from the transit depth, was slightly larger than Jupiter. Together, the data revealed a world firmly in the category of hot Jupiters, circling its star at a distance only a few million kilometers away. The planet was named TRES 2b, the second discovery of the survey, but it would soon become far more famous than its modest name suggested. At first, TRES 2b appeared typical of its class. Many hot Jupiters had already been found, and their close orbits, large sizes, and high temperatures made them relatively easy targets for transit surveys. What distinguished TRES 2b was not its orbit or mass, but what astronomers discovered when they looked more closely at its brightness. Using the Kepler spacecraft, which launched in 2009 and happened to include the star among its monitored field, astronomers gathered data of unprecedented precision. Kepler's detectors measured stellar brightness to better than 1 part in 10,000, far beyond the capability of ground-based telescopes. With this precision, astronomers could not only confirm the transits of TRES 2b, but also measure its albedo. The result was astonishing. When the planet passed behind its star in a secondary eclipse, there was almost no difference in brightness. The expected signal of reflected light was missing. The albedo was calculated to be less than 1%. This meant that the planet was darker than any world known, reflecting less light than charcoal or asphalt. Even compared to the darkest regions of our moon, TRES 2b absorbed more and reflected less. To call it pitch black was no exaggeration. It was, by the numbers, the darkest exoplanet ever measured. The implications rippled quickly through the scientific community. For years, astronomers had assumed that hot Jupiters, like Jupiter itself, might be adorned with reflective clouds. Yet TRES 2b showed none. Its skies were evidently free of bright condensates, replaced instead by molecules that devoured visible light. This finding forced a re-evaluation of how heat, chemistry, and atmospheric dynamics operate in extreme environments. It suggested that high temperatures close to the star could prevent clouds from forming at all, leaving behind only absorptive gases like sodium and potassium, or even exotic compounds like vaporized titanium oxide. To the public, the story was equally compelling. A planet darker than coal, orbiting a distant star, captured imaginations around the world. Headlines spoke of a world as black as ink, a cosmic shadow hiding in plain sight. For once, the metaphor matched the measurement, and people marveled at the idea that nature could produce such a place. Scientists, while careful to emphasize the numbers, also recognized the value of this fascination. The discovery of TRES 2b was not only a scientific milestone, but also an opportunity to share the wonder of astronomy with a broader audience. TRES 2b remains a touchstone in the study of exoplanets. It reminds us that light, though a universal messenger, can sometimes return almost empty-handed. It shows that planets can be stranger than models predict, darker than intuition allows, and it sets the stage for deeper questions. What exactly makes a world so black? So, how do its atmospheric molecules interact with photons? What lessons can it teach us about planets elsewhere, and even about the processes that shaped our own solar system? The discovery of TRES 2b was more than a catalogue entry. It was a turning point, a case study in the unexpected, and a harbinger of the complexities yet to come. As astronomers studied it further, they would begin to untangle the physics behind its darkness, uncovering not just the nature of one world, but insights into the behavior of many. The confirmation of TRES 2b's extraordinary darkness owed much to the capabilities of the Kepler spacecraft. From its vantage point in space, Kepler avoided the atmospheric distortions that blur ground-based measurements. It was designed to monitor more than 150,000 stars continuously, detecting the tiny dips in brightness caused by planetary transits. In the case of TRES 2b, this precision made it possible to go beyond simply measuring size and orbit. By recording the minute changes in brightness as the planet orbited, Kepler could also detect the combined effects of reflected light and emitted heat. What astronomers expected was at least a faint signature of reflection. Even a hot Jupiter with few clouds should scatter some light, producing a detectable secondary eclipse when the planet slipped behind its star. Yet when the data were analyzed, the difference was vanishingly small. The reflected component was almost non-existent. The calculations yielded an albedo of less than 1%, a value so low it defied ordinary comparison. For context, fresh asphalt reflects about 4% of sunlight, charcoal around 5%, and the moon's darkest craters about 7%. TRES 2b reflected less than any of these. It was darker than the blackest natural surface measured on Earth. Still, Kepler's measurements also revealed that the planet was not entirely invisible. While it reflected almost no visible light, it emitted a faint glow in the infrared, heat radiating from its superheated atmosphere. This distinction was crucial. TRES 2b was not a dead, cold object, but a living system in thermodynamic balance, absorbing immense energy from its star and re-radiating it outward. The fact that it glowed in infrared while remaining nearly invisible light, underscored the importance of studying multiple wavelengths. Darkness, in this case, did not mean absence of energy. It meant selective absorption and emission, a planetary atmosphere tuned to swallow visible photons and release them as heat. The next question was why. Theorists considered several possibilities. The most straightforward explanation was the absence of reflective clouds. On Jupiter and Saturn, high-altitude clouds of ammonia crystals scatter sunlight efficiently, giving the planets their bright appearance. But on TRES 2b, orbiting so close to its star that temperatures soared above 1,000 degrees Celsius, such clouds could not form. Any condensates would vaporize, leaving the atmosphere bare. In their place, atoms of sodium and potassium, both strong absorbers in the visible spectrum, could dominate. More exotic still, molecules like titanium oxide or vanadium oxide might be present, each capable of absorbing vast amounts of light. These hypotheses painted a picture of an atmosphere stripped of mirrors and filled with absorbers, a perfect recipe for darkness. Some models suggested that high temperatures might even ionize parts of the atmosphere, changing its opacity in ways not yet fully understood. Others pointed to the possibility of vertical mixing, where heat from below prevented the formation of stable cloud layers. In each scenario, the message was the same. Extreme proximity to the parent star produced conditions so alien that traditional expectations no longer applied. TRES 2b was not simply a darker version of Jupiter. It was a different category of world altogether. As the findings circulated, scientists worked to verify them with additional instruments. The Spitzer Space Telescope, operating in the infrared, confirmed the planet's heat signature. Ground-based telescopes attempted to replicate the phase curve measurements, though with less precision than Kepler. Each line of evidence pointed in the same direction. TRES 2b was almost completely dark in visible light, but warm and glowing in infrared. Its strangeness was undeniable, its place as the darkest known planet secure. The discovery also raised broader questions. Was TRES 2b unique, or was it simply the first well-measured example of a class of ultra-dark worlds? If other hot Jupiters shared its properties, then planetary albedo was not just a curiosity, but a crucial test of atmospheric theory. Darkness, in this sense, was not an exception, but a data point along a spectrum. Each new measurement would either reinforce TRES 2b's singularity or reveal it as part of a wider pattern. In the years that followed, additional low albedo planets were indeed found, though none quite as extreme as TRES 2b. This confirmed that while rare, darkness at this level was not an observational mistake. It was a genuine outcome of planetary physics. Theorists refined their models accordingly, incorporating new chemistry and dynamics to explain how starlight could vanish so completely into a planetary atmosphere. For the scientific community, TRES 2b became a benchmark, a planet against which models could be tested and instruments calibrated. For the public, it was an emblem of the unexpected. A world darker than coal, orbiting a star like our Sun, seemed almost like a contradiction in terms, yet it was real, measured, and confirmed by multiple lines of evidence. In its darkness lay both a challenge and a promise. The challenge was to understand how nature could produce such a world. The promise was that if one planet could surprise us so profoundly, countless others might do the same. Thus, the discovery of TRES 2b was more than a curiosity. It was a revelation that even the simplest property of a planet, how much light it reflects, could lead to profound questions about chemistry, physics, and the diversity of worlds. And it prepared astronomers to look more closely, to peel back the layers of darkness and uncover the processes that govern this strange and remarkable planet. The full significance of TRES 2b's discovery only came into focus as astronomers reflected on what it meant for the wider field of planetary science. Until then, Hot Jupiters had often been treated as exotic, but somewhat predictable. Their orbits were tight, their atmospheres scorched, and their physical sizes broadly comparable. They were considered a family of planets with shared characteristics, useful as laboratories for testing detection methods, but not expected to hold deep surprises. TRES 2b shattered that assumption. By being darker than any other planet, it revealed that even within the apparently narrow category of hot Jupiters, nature could produce extremes that defied easy explanation. The precision of Kepler's photometry ensured that this was not a fluke. Night after night, the spacecraft recorded the star's brightness, tracing the repeated dips of transits and the nearly imperceptible absence of reflected light. The data left little room for doubt. What was astonishing was not only the measurement itself, but also the contrast with Jupiter, the archetype of the class. Jupiter reflects about half of the sunlight that strikes it, making it one of the brightest objects in the solar system. TRES 2b, similar in size, reflected less than 1%. Two planets of comparable scale, governed by the same physical laws, had albedos separated by more than a factor of 50. Such a disparity demanded explanation, and it forced theorists to admit that the diversity of exoplanets was far greater than models had predicted. The importance of this discovery went beyond atmospheric chemistry. It also demonstrated the power of continuous monitoring from space. Ground-based surveys like TRES had been able to detect the transit of TRES 2b, but only with the precision of Kepler could its albedo be measured so definitively. This revealed the potential of future missions to uncover not just planets but detailed properties, transforming exoplanet science from detection to characterization. TRES 2b became a proof of concept, showing that with the right instruments, astronomers could read the reflectivity, temperature, and even circulation of alien skies. Within the scientific community, the discovery sparked debates about classification. Should TRES 2b be considered a normal hot Jupiter with an unusual albedo, or did its extreme darkness mark it as a separate category altogether? Some argued that it was simply an outlier on a spectrum, while others suggested that ultra-dark planets might represent a distinct family shaped by unique atmospheric processes. Whatever the conclusion, the debate itself underscored how much remained unknown. Exoplanet science was still young, and each extreme case carried disproportionate weight in shaping the field. Public fascination kept pace with scientific curiosity. When news of a planet darker than coal spread, it captured imaginations in ways few other discoveries had. Artists rendered it as a black marble orbiting a yellow star, a ghostly silhouette, with only a faint crimson glow from its heated atmosphere. While such images were speculative, they helped convey the strangeness of the data. For non-specialists, it was easier to grasp darker than charcoal than albedo, less than 1%. The discovery highlighted how metaphors and measurements together could communicate the wonder of science. It also showed how darkness, often a symbol of ignorance or fear, could be reclaimed as a sign of discovery and knowledge. TRES 2b quickly became a target for follow-up. Observers sought to refine its orbital parameters, confirm its temperature, and search for any wavelength at which it might reflect more strongly. Infrared data confirmed that while invisible in visible light, the planet glowed warmly, consistent with an atmosphere heated to more than 1,000 degrees Celsius. The absence of reflection was not the result of missing the planet entirely. It was a true property of its atmosphere, a fingerprint of its composition. Each observation reinforced the conclusion, adding confidence and sharpening the mystery. As more dark exoplanets were found, TRES 2b retained its title as the darkest. It became a reference point, cited in papers and lectures, as the benchmark of planetary absorption. Its story was woven into textbooks and popular accounts, ensuring that it would remain one of the most famous exoplanets of the early 21st century. For astronomers, it was both a puzzle and an opportunity. By confronting the conditions that produced such extreme darkness, they could test models of atmospheric physics under pressures and temperatures impossible to reproduce on Earth. By explaining TRES 2b, they could better understand the mechanisms that shape the diversity of exoplanets as a whole. The discovery also carried a subtle philosophical lesson. It reminded scientists that the universe does not conform to human expectations. Even properties as basic as brightness can defy prediction. A planet the size of Jupiter, orbiting a star much like the Sun, could appear as black as ink. This was not a contradiction, but a revelation, a reminder that science advances not by confirming what we expect, but by confronting what surprises us. In the end, the discovery of TRES 2b was both an endpoint and a beginning. It was the culmination of the TRES survey, a testament to the ingenuity of small telescopes working in concert across oceans. But it was also the start of a new line of inquiry, one that would carry astronomers deeper into the physics of planetary darkness. The next step was to ask how, at the molecular level, such a world could exist. What physical processes shaped its atmosphere? What made it so different from Jupiter, Saturn, or any of the gas giants we knew? These questions would define the next chapter in the story, as scientists turned from discovery to explanation, from the fact of darkness to the physics behind it. To understand why TRES 2b is so dark, one must begin with the physics of albedo itself. A planet's brightness is not determined only by how much starlight reaches it, but by what happens to that light when it encounters the planet's atmosphere and surface. Light can be scattered back into space, absorbed by molecules, or transmitted deeper before being re-emitted as heat. The balance among these processes decides whether a world shines like Venus, glimmers like Earth, or fades into obscurity, like TRES 2b. In many cases, clouds dominate this balance. On Jupiter, for instance, high layers of ammonia crystals scatter sunlight efficiently, giving the planet its pale appearance. On Earth, water clouds contribute much of the planet's 30% reflectivity. Clouds are mirrors in the sky, brightening planets wherever they form. TRES 2b orbits so close to its star that temperatures in its upper atmosphere soar well above 1,000 degrees Celsius. At such extremes, familiar clouds cannot exist. Ammonia, water, and methane, all common cloud formers in cooler gas giants, would be vaporized, unable to condense into reflective layers. Without these bright mirrors, the atmosphere is stripped down to gases that interact with light in darker ways. Sodium and potassium atoms, abundant in hot environments, absorb strongly in the visible spectrum. Titanium oxide and vanadium oxide, molecules that act almost like pigments, soak up vast amounts of starlight. The result is an atmosphere primed not to reflect, but to consume photons. This absorption is enhanced by the very heat that prevents cloud formation. High temperatures not only vaporize condensates but also excite molecules, broadening their absorption lines and making them more efficient at capturing light. In laboratory conditions, sodium and potassium produce sharp absorption features, narrow windows where photons are swallowed. In the furnace of a hot Jupiter, these lines blur and merge, expanding across the visible spectrum. Instead of a few dark bands, the atmosphere becomes a near-continuous absorber, robbing the planet of brightness across nearly all wavelengths. What reaches our telescopes is not reflection, but a faint thermal glow shifted into the infrared. Another factor is atmospheric circulation. On a tidally locked planet like TRES 2b, one hemisphere faces perpetual day, while the other lies in endless night. This creates steep temperature gradients, driving winds of thousands of kilometers per hour that redistribute heat. Such circulation can prevent stable cloud layers from forming, mixing the atmosphere so thoroughly that condensates are swept away before they can gather. The skies remain clear, but not clear in the way of a blue, earthly sky. They are clear in the sense of being stripped of reflective particles, leaving only a dark, absorbing gas envelope. Comparisons to Jupiter highlight the difference. Jupiter's reflectivity is not inherent to its bulk composition, but to its weather systems. Remove the clouds, and Jupiter would be much darker. TRES 2b demonstrates what happens when a gas giant is stripped of cloud decks entirely. Instead of gleaming with white bands, it becomes a smoldering ember, almost invisible against its star, invisible light. The contrast underscores how profoundly environment shapes planetary appearance. Similar size, similar mass, but utterly different. Albedo, This is the lesson of TRES 2b. Scientists have tested these ideas with atmospheric models, using computer simulations to predict how different gases absorb and scatter light at extreme temperatures. These models confirm that sodium, potassium, and titanium oxide can indeed produce very low albedos when clouds are absent. They also suggest that high-altitude hazes, made of complex hydrocarbons or metal compounds, could deepen the darkness further. Instead of scattering sunlight like smoke or mist on Earth, these hazes absorb it, acting more like a veil of soot than a layer of fog. The confirmation of these processes came not from imagination but from observation across multiple wavelengths. While TRES 2b is almost invisible in visible light, it glows in the infrared, consistent with heat emission from a planet bathed in stellar radiation. Spitzer detected this faint thermal glow, showing that the planet's dayside reaches temperatures well over 1,000 degrees Celsius. The absence of reflection combined with strong infrared emission confirmed the picture: a world that swallows starlight and re-radiates it as heat, a planetary blackbody more efficient than almost any natural surface known. This strange behavior is not without precedent in physics. On Earth, materials like carbon nanotube forests or vantablack coatings absorb more than 99% of incoming light. These are engineered substances, designed to be as dark as possible. TRES 2b achieves something similar not by engineering but by chemistry and heat. An atmospheric vantablack forged by nature, it is a reminder that the laws of physics apply universally and that the cosmos can produce outcomes as extreme as our laboratories, if not more so. For astronomers, TRES 2b provides a chance to study absorption under conditions unreachable on Earth. Pressures thousands of times greater than Earth's atmosphere, temperatures exceeding 1,000 degrees, radiation levels beyond any laboratory lamp. This is the crucible in which its darkness is forged. By modeling how light interacts with matter under such conditions, scientists refine not only their understanding of exoplanets but also their grasp of atomic and molecular physics. TRES 2b thus becomes more than an oddity. It becomes a natural laboratory, a place where theory meets reality under the most unforgiving circumstances. And yet, questions remain. Could hidden, reflective layers exist deeper in the atmosphere, unseen by current instruments? Could transient clouds form on the night side only to be destroyed as they circulate into the dayside heat? Might exotic processes, unknown to earthly chemistry, play a role? Each possibility awaits further data, and future telescopes with greater sensitivity may provide answers. For now, what is certain is that TRES 2b forces us to reconsider what it means for a planet to be visible. Brightness, we learn, is not guaranteed. Darkness can be just as real, just as revealing, and just as beautiful in its own way. The chemistry that shapes TRES 2b's darkness is a story of molecules under fire. In the calm conditions of Earth's atmosphere, water condenses into clouds, carbon dioxide absorbs in narrow bands, and sunlight scatters off air molecules to create the blue of the sky. But at the temperatures of a hot Jupiter, these familiar processes unravel. Water cannot remain liquid or solid. Methane, a major absorber in cooler planets like Neptune, breaks apart. Instead, heavier atoms and molecules dominate, altering the optical fingerprint of the atmosphere. Sodium and potassium, two of the simplest elements, emerge as key players. At high temperatures, they exist as gases, free to interact with photons. Both elements absorb strongly in the visible spectrum, imprinting broad features that overlap and combine when heated. In laboratory experiments, sodium vapor lamps glow with a bright yellow line, while potassium lamps glow red. On TRES 2b, these same atoms, spread throughout a thick atmosphere and heated to more than 1,000 degrees Celsius, act not as emitters, but as absorbers, devouring starlight that would otherwise escape. The result is an atmosphere tuned to darkness, an absorber so efficient it erases the faint glow we might expect. More exotic still are molecules like titanium oxide and vanadium oxide. These compounds, familiar to chemists as pigments and catalysts, become gaseous in the furnace of a hot Jupiter. Unlike sodium and potassium, which absorb in specific bands. Titanium oxide and vanadium oxide absorb broadly across the visible spectrum. In the atmospheres of some hot planets, they are thought to create temperature inversions, layers where the air becomes hotter with altitude instead of cooler. On TRES 2b, their presence could help explain the planet's almost total lack of reflection. The combination of alkali metals and metal oxides paints the atmosphere black, not with clouds or soot, but with chemistry itself. Yet darkness is not uniform. Models suggest that TRES 2b's night side may be cooler, potentially allowing transient condensates to form. If clouds or hazes appear on the night side, they may brighten the planet slightly before being swept into the day side and destroyed by heat. Such a cycle could produce subtle variations in brightness, detectable only with the most precise phase curve observations. Detecting such changes would reveal not just composition, but weather and alien meteorology written in light and shadow. The influence of the parent star cannot be overstated. TRES 2b orbits so close that it receives hundreds of times more radiation than Earth does from the Sun. This radiation not only heats the atmosphere, but also bombards it with ultraviolet light, breaking apart molecules and driving complex chemical reactions. Photochemistry at these levels is unfamiliar territory, producing species that may not exist naturally on Earth. Hydrocarbons, nitriles, and even metallic compounds could form, adding to the absorbing haze. The star is both the planet's light source and its sculptor, shaping an atmosphere that reflects almost nothing back into space. Laboratory comparisons help anchor these ideas. On Earth, scientists can heat small chambers of gas to high temperatures and measure how they absorb light. Sodium and potassium absorption has been studied this way for decades, originally to understand the spectra of stars. Titanium oxide too has been measured, its absorption curves well known to chemists. But translating laboratory data into planetary atmospheres is never simple. Pressures on TRES 2b are far higher than any chamber can reproduce, and mixtures of gases behave differently than pure samples. Models must extrapolate, guided by theory and experiment alike, but always aware of the uncertainty. This is why exoplanets are so valuable. They are natural laboratories that test physics in ways no machine on Earth can. The extreme conditions of TRES 2b also provide a glimpse into processes that may operate in other environments. Brown dwarfs, the failed stars that bridge the gap between giant planets and stars, have atmospheres rich in alkali metals and metal oxides. Understanding TRES 2b sheds light on these objects as well. Even stellar atmospheres, where temperatures and pressures soar, show similar absorption features. The physics of darkness on one exoplanet thus reverberates across astrophysics, linking planets, brown dwarfs, and stars into a continuum of atmospheric science. At the heart of this work lies a paradox. To study a planet as dark as TRES 2b, astronomers must rely on light. It is only by measuring the faint infrared glow, the absence of reflection, and the subtle shifts in brightness as the planet orbits that its properties can be deduced. Light reveals the absence of light, a contradiction only in appearance. In truth, it is the precision of light's message that makes such studies possible. Every photon absorbed leaves a gap. Every photon emitted leaves a clue. From these gaps and clues, the portrait of darkness is assembled. Theorists continue to refine models, comparing predictions with the Kepler data and later observations. Some suggest that even darker worlds may exist, their atmospheres filled with compounds that absorb across wider bands. Others predict that variations in metallicity, the abundance of heavy elements, could create differences in albedo from one planet to another. TRES 2b may not be unique, but simply the first extreme case to be measured. If so, then the catalogue of exoplanets may one day reveal a family of worlds that swallow starlight as efficiently as engineered black materials on Earth. For now, what stands out is the role of chemistry, radiation, and heat working together to erase reflection. In TRES 2b, clouds are absent, absorbers are abundant, and circulation prevents brightening. The planet's darkness is not an accident, but a consequence of physics pushed to its limits. By studying it, astronomers do more than explain a curiosity. They learn how matter behaves when bathed in starlight far stronger than any we know, how molecules absorb and radiate under pressures and temperatures beyond earthly reach. And in doing so, they remind us that even the simplest question, why is this planet dark, can lead to some of the deepest answers in astrophysics. The case of TRES 2b illustrates how planetary science is not only about cataloguing orbits and masses, but about confronting the extremes of nature. When astronomers first measured its near-zero albedo, the instinct was to search for comparison. Could any world in the solar system provide a hint of such darkness? The answer was no. Even the charred basalt of the Luna Maria reflects more light. Even the soot-darkened surfaces of comets glimmer faintly. TRES 2b stands beyond these references, a reminder that the physics of light can yield results that earth-bound intuition fails to predict. In the laboratory, engineers have created materials that rival this darkness. Forests of carbon nanotubes and coatings like Vantablack absorb more than 99% of light. These materials achieve their effect by trapping photons within intricate microstructures, forcing them to bounce and scatter until their energy is dissipated as heat. On TRES 2b, a different mechanism produces a similar outcome. Instead of geometry, it is chemistry and heat that erase reflection. The comparison is imperfect, but striking. What humans have engineered in controlled environments, nature has achieved on a planetary scale, sculpting a world that swallows nearly every photon that strikes it. Theoretical work has explored whether such extreme absorption might have secondary consequences. A planet that reflects almost nothing must absorb and re-radiate vast amounts of energy. This alters circulation, driving intense winds and possibly redistributing heat unevenly between the day and night sides. Some models predict that hot Jupiters like TRES 2b could exhibit thermal contrasts of hundreds of degrees Celsius between their hemispheres. The day side, locked in perpetual noon, glows in infrared, while the night side, though cooler, still radiates strongly compared to Earth standards. These dynamics may even feed back into atmospheric chemistry, creating or destroying molecules depending on their location in the circulation pattern. Darkness is not just a surface property. It is woven into the climate of the entire planet. Another avenue of investigation concerns the possibility of spectral windows, narrow ranges of wavelengths where reflection might occur, even in a generally dark atmosphere. On TRES 2b, astronomers search carefully for such glimmers, hoping to catch scattered light in the blue or red ends of the spectrum. Thus far, no convincing signal has appeared. The darkness seems complete across the visible range, but the search continues, for even a tiny detection could refine models and point to specific molecules at work. In this way, darkness is not a barrier, but a challenge, an invitation to push instruments to their limits. The broader lesson is that albedo cannot be predicted simply from size, mass, or distance to a star. It depends critically on chemistry, cloud formation, and heat balance, factors that vary from one world to another in ways we are only beginning to grasp. TRES 2b underscores this point vividly. Two planets of similar mass, Jupiter and TRES 2b, differ in albedo by more than 50-fold. The difference arises not from fundamental physics, but from context. One orbits far from its star in the cold outer solar system. The other bakes in relentless starlight. Context is destiny, and in this case, destiny is darkness. Future missions will test these ideas further. The James Webb Space Telescope, with its ability to observe in infrared at high precision, is capable of probing the thermal emission of dark exoplanets in unprecedented detail. The European Space Agency's Ariel mission, planned for launch in the next decade, is designed specifically to study planetary atmospheres across a wide sample, measuring absorption and reflection to build a comparative framework. By studying dozens of hot Jupiters and their cooler cousins, scientists will learn whether TRES 2b is an extreme outlier or a representative of a larger class of ultra-dark worlds. Even as technology advances, the philosophical impact of such discoveries remains. Darkness, long a metaphor for ignorance or absence, becomes here a source of knowledge. To measure that a planet reflects less than 1% of starlight is not to lament a lack of data, but to celebrate the precision of our instruments. The universe tells its story not only in bright signals but in silences, in the photons that fail to return as well as those that do. TRES 2b reminds us that absence itself can be evidence, that the void has structure, and that the cosmos does not owe us brilliance in order to be understood. By the end of the second decade of the 21st century, TRES 2b had become a touchstone in exoplanet science, cited in nearly every discussion of albedo. It demonstrated that reflectivity is not guaranteed, that planets can be as dark as engineered materials, and that chemistry, under extreme conditions, can reshape our expectations. Its existence continues to shape theory, guide observation, and inspire new questions about the limits of planetary diversity. And so, from a modest network of small telescopes to the unparalleled precision of Kepler, from simple measurements of brightness to complex models of chemistry, the story of TRES 2b's darkness has unfolded. It shows us that light can reveal not only brilliance but also the near absence of reflection, and that even in that absence, the universe speaks. The next step is to place TRES 2b in context, to ask whether it is alone or one of many, and to explore how other low albedo worlds deepen our understanding of planetary atmospheres. TRES 2b may hold the title of the darkest known planet, but it is not alone in teaching astronomers about the limits of reflectivity. In the years following its discovery, other hot Jupiters revealed themselves to be strikingly dim, though none quite so extreme. Each new case added weight to the idea that darkness is not an anomaly but a recurring theme among certain classes of exoplanets. By studying these worlds together, scientists have begun to map the range of possible albedos, linking chemistry, temperature, and stellar environment to the reflectivity we observe. One of the earliest confirmations came from the Kepler mission itself. With its unparalleled precision, Kepler measured phase curves for several hot Jupiters. Among them were planets that reflected surprisingly little light, with albedos under 10%. These values were far lower than Jupiter's 50% or even Earth's 30%, but higher than the near zero of TRES 2b. The data suggested a spectrum of darkness, with some hot Jupiters appearing dim but not invisible, and others pushing into near total absorption. Each planet provided a point on this curve, helping to define the boundaries of planetary physics. The Hubble Space Telescope added further detail. By observing in multiple wavelengths, Hubble could distinguish between light scattered in the blue and light absorbed in the red. Some hot Jupiters, like HD 189733b, showed hints of Rayleigh scattering, the same process that makes Earth's sky blue, suggesting the presence of small particles high in the atmosphere. These planets appeared somewhat brighter in blue light than in red, producing modest albedos. Others, like WASP 12b, appeared dark across the spectrum, consistent with atmospheres dominated by absorbing molecules. Each case told a slightly different story, but together they reinforced the idea that clouds and hazes are the key. Where they form, planets brighten. Where they fail, planets darken. The Spitzer Space Telescope, operating in the infrared, provided complementary insights. By measuring heat emission, Spitzer showed that many of the darkest planets were also among the hottest. Their day sides glowed intensely in infrared even as their visible reflection was nearly absent. This confirmed that energy was not missing, but redistributed, absorbed, and re-radiated as thermal light. The contrast between visible darkness and infrared brightness became a hallmark of ultra-hot Jupiters, teaching astronomers that albedo is only part of the story. To understand a planet fully, one must measure both the light it reflects and the heat it emits. Comparisons to our own solar system remained instructive. Jupiter and Saturn, bright in visible light, owe their albedos to reflective clouds of ammonia and other condensates. Without those clouds, their underlying atmospheres would be much darker. Hot Jupiters close to their stars exist in conditions where such clouds cannot survive, and their darkness is the natural consequence. TRES 2b sits at the extreme, but the trend is clear. High temperature suppresses cloud formation, and suppressed clouds mean low albedo. Still, not all hot Jupiters conform to this pattern. Some, despite high temperatures, show evidence of reflective clouds made of silicates or metal oxides. Kepler 7b, for example, has an unusually high albedo compared to its peers, likely due to bright cloud decks in its upper atmosphere. This diversity highlights the complexity of atmospheric processes. Temperature alone does not decide albedo. Composition, circulation, and stellar radiation all play roles. The result is a menagerie of worlds, some gleaming, some dim, each shaped by a unique balance of forces. As the catalogue of exoplanets has grown, the importance of measuring albedo has only increased. Every new dark planet adds evidence to the emerging framework, showing how absorption dominates under certain conditions. Every brighter one adds nuance, reminding us that exceptions exist. The science of planetary reflectivity is not about single cases, but about patterns, and TRES 2b, while extraordinary, is part of a larger tapestry. The search for low albedo worlds continues with new tools. The James Webb Space Telescope, launched in 2021, brings unmatched sensitivity across infrared wavelengths. It can detect heat signatures with precision never before possible, probing the energy budgets of hot Jupiters in detail. The European Space Agency's ARIL mission, planned for the late 2020s, will survey hundreds of exoplanet atmospheres, providing systematic measurements of reflection and emission. Together, these observatories promise to reveal whether TRES 2b is truly exceptional or simply one member of a broader family of dark giants. The lesson so far is that darkness is not rare. It is part of the diversity of planets, a natural outcome of atmospheres heated, stripped, and reshaped by their stars. To measure a planet's albedo is not just to assign a number, but to glimpse the physics of its skies. TRES 2b may be the darkest, but it stands among others that share its fate, each one a reminder that the cosmos is not obliged to shine for our convenience. The story of low albedo planets widened as astronomers accumulated more precise measurements from both Kepler and ground-based observatories. Each new detection added another piece to the puzzle of why some worlds blaze brightly, while others remain shrouded in near blackness. One striking example was WASP-12b, a planet discovered in 2008, orbiting so close to its star that it completes a year in just over one Earth day. Its atmosphere is heated to more than 2,500 degrees Celsius, hot enough to vaporize many molecules that would otherwise form clouds. Observations revealed that WASP-12b reflects almost no visible light, with an albedo measured at only a few percent. Like TRES 2b, it absorbs almost everything, re-radiating energy only as infrared glow. The finding reinforced the idea that extreme heat prevents the formation of reflective condensates, stripping these planets of the brightness we see in cooler giants. Another case is WASP-19b, an inflated hot Jupiter orbiting a G-type star. Phase curve observations with Hubble and Spitzer showed that it too reflects very little visible light. Its darkness was attributed not just to missing clouds, but to chemical processes in the upper atmosphere that produce absorbing hazes. These hazes act less like reflective aerosols and more like a layer of soot, capturing photons rather than scattering them. The comparison between WASP-12b and WASP-19b demonstrated that even among very hot planets, different processes could conspire to produce similar darkness. One lacked clouds because of sheer heat. The other developed absorptive hazes. The end result in both cases was a world that swallowed starlight. Kepler provided still more examples. Among its thousands of candidates were planets like Kepler 77b and Kepler 13ab, both of which showed unusually low albedos. Kepler 77b, with an albedo near 0.3%, was confirmed as one of the darkest worlds after TRES 2b. Kepler 13ab presented a complex case, with brightness varying across wavelengths, suggesting a combination of dark absorption and patchy reflective clouds. These variations reminded astronomers that albedo is not a single fixed property but can vary with time, location, and wavelength. A planet might be dark overall but reveal bright patches, or it might reflect selectively in blue while absorbing in red. Each case added texture to the science, showing that planetary darkness is not monolithic. The growing list of dark planets highlighted another challenge: observational uncertainty. Measuring albedo across light years is inherently difficult, and small errors can shift values dramatically. Stars fluctuate, instruments drift, and data processing introduces noise. For this reason, every claim of a low albedo is scrutinized carefully. Repeated observations with independent instruments are essential. TRES 2b's near-zero value holds up precisely because it has been confirmed across multiple methods and telescopes. Other planets may appear extremely dark in one dataset, but somewhat brighter in another, a reminder of the delicate nature of the work. Yet even with uncertainties, a pattern emerges. The hottest planets, those orbiting close to their stars with dayside temperatures exceeding 2,000 degrees Celsius, are almost always dark. The lack of clouds, the presence of gaseous absorbers, and the constant bombardment of stellar radiation create the perfect recipe for low reflectivity. Cooler giants farther from their stars tend to be brighter, their atmospheres capable of supporting clouds of water, ammonia, or methane. Between these extremes lies a spectrum, where brightness and darkness shift according to chemistry, temperature, and circulation. TRES 2b is at the darkest end, but it is part of a continuum rather than a solitary outlier. These findings also highlight the limitations of analogies to the solar system. Jupiter and Saturn may seem like natural benchmarks, but their high reflectivity is a product of cold, cloud-filled atmospheres. Hot Jupiters like TRES 2b and WASP 12b show that under different stellar conditions, giants can look utterly different. The diversity of albedos across exoplanets warns against assuming that our local examples are universal. Instead, each planet must be studied on its own terms, its reflectivity read as the product of unique circumstances. By the early 2020s, the catalogue of low albedo worlds had grown large enough to suggest that darkness was not an exception, but a rule for many close-in giants. TRES 2b remained the darkest, but it was no longer alone. Each new discovery reinforced the view that albedo is a diagnostic tool, revealing atmospheric processes invisible by other means. To measure the darkness of a planet is to probe its chemistry, its dynamics, and its interaction with starlight. The blacker the world, the more extreme the conditions that shape it. And so, the study of other low albedo planets placed TRES 2b in context. It was not a solitary marvel, but the darkest example of a broader trend. This recognition transformed the discovery from a curiosity into a cornerstone, a benchmark against which all other dim planets are compared. As new instruments refine measurements and expand the sample, the tapestry of darkness grows richer, each planet adding detail to the portrait of how light and matter dance across the galaxy. The effort to understand other low albedo worlds is also an effort to confront the limits of observation itself. Every claim about planetary darkness rests on the delicate balance between signal and noise, between what the telescope records and what astronomers infer. A planet reflecting only a fraction of a percent of starlight produces a vanishingly small signal. To measure it requires instruments of exquisite stability and teams of scientists devoted to extracting faint patterns from overwhelming glare. Even then, caution is essential. Stars are not constant. They pulsate, flare, and shift, creating brightness variations that can mimic or obscure the signature of a planet. Detectors, no matter how advanced, introduce their own imperfections. The challenge is to separate the planetary fingerprint from this background. This is why phase curves and secondary eclipses are studied with such care. A single measurement is never enough. Repeated observations across many orbits are required, building confidence that the faint dip in brightness when a planet passes behind its star is real. By stacking data, aligning it carefully, and comparing across instruments, astronomers gain the certainty needed to declare a planet dark. TRES 2b earned its reputation through precisely this process. Its near-zero albedo was not guessed from one observation, but confirmed across many by both Kepler and follow-up studies. Other planets, though also dim, often lack the same wealth of data, leaving their exact reflectivities less certain. The uncertainties are not a weakness but part of the scientific process. Each error bar marks the frontier of knowledge, the line between what is known and what remains tentative. In this way, the study of low albedo planets mirrors the broader story of astronomy itself, a discipline where confidence is built slowly, photon by photon, through the convergence of independent results. The more instruments that confirm a measurement, the firmer it becomes. And as new telescopes come online, these uncertainties will shrink, sharpening the picture of planetary darkness. Future missions promise a revolution in this field. The James Webb Space Telescope, with its ability to measure both visible and infrared light with unprecedented precision, is already probing the atmospheres of hot Jupiters. It can detect faint thermal emission, distinguish between molecular absorbers, and map heat distribution across dayside and nightside. For low albedo planets, this means not only confirming their darkness, but understanding the exact chemistry behind it. Where Kepler showed the absence of reflection, Webb can reveal what absorbs the light instead. The Ariel mission, expected later in the decade, will expand this work by surveying hundreds of planets systematically, creating a statistical framework for albedo across a wide range of temperatures and compositions. Ground-based observatories will also play their role. The coming generation of extremely large telescopes, with mirrors spanning more than 30 meters, will push photometry to new levels. Their adaptive optics systems will cut through atmospheric distortion, allowing precise brightness measurements even from Earth. Combined with space-based observatories, they will provide continuous coverage, refining phase curves, and secondary eclipses across wavelengths. In this synergy, the darkness of planets like TRES 2b will be studied not as isolated curiosities, but as case studies within a broader landscape. The scientific implications of these studies reach far beyond aesthetics. Darkness is not merely an absence of reflection. It is a marker of atmospheric chemistry, a constraint on cloud formation, a clue to circulation and energy balance. A planet that reflects almost nothing tells us that condensates cannot survive, that absorbers dominate, and that stellar radiation sculpts the atmosphere in radical ways. Each low albedo measurement narrows the range of possible models, forcing theorists to refine their understanding of heat transport, photochemistry, and atmospheric dynamics. The result is a more accurate map of how planets behave across environments unimaginable on Earth. At the same time, these discoveries remind us of the diversity of worlds. Not all hot Jupiters are dark. Some gleam with reflective clouds, others glow faintly in selective wavelengths. The contrast between bright planets like Kepler 7b and dark ones like TRES 2b shows that planetary albedo is not dictated by size alone, but by the interplay of heat, composition, and weather. This diversity prevents easy generalization, but enriches the science, turning every new planet into a test case for theory. In the cultural imagination, darkness carries metaphorical weight. To call a planet darker than coal evokes mystery and awe, a sense of the unknown lurking in the cosmos. Yet in astronomy, darkness is not a void but a measurement, a number that speaks of chemistry and physics. It is evidence, not absence. By reframing darkness in this way, science turns metaphor into knowledge, revealing that even the blackest worlds are rich with information. Thus, the study of other low albedo planets transforms TRES 2b from an outlier into a benchmark. It shows that darkness, while extreme in its case, is part of a continuum of outcomes shaped by stellar heat and atmospheric composition. It teaches that every photon not reflected carries meaning, and that the absence of light can be as informative as its presence. And it prepares us for the discoveries yet to come, when new instruments will reveal still more worlds, each with its own relationship to light and shadow. The chapter of darkness does not end with TRES 2b. It expands into a gallery of planets, each one adding depth to our understanding. Together they remind us that the universe is not uniform but diverse, not predictable but inventive. And in that diversity lies the true power of astronomy, to see not only what shines, but also what does not, and to learn from both. Detecting a planet that reflects almost no light is like searching for a whisper in a thunderstorm. The glare of the host star is so overwhelming that the faint contribution of the planet seems all but impossible to extract. And yet astronomers have learned to do precisely this, building methods that turn the noise of starlight into the signal of worlds. The story of observing the invisible is not only about the planets themselves, but about the ingenuity of the instruments and minds that reveal them. The first challenge is contrast. A star like the Sun outshines its planets by billions of times in visible light. Even a reflective planet would appear as a faint echo beside this brilliance. For a world like TRES 2b, which reflects almost nothing, the task is harder still. The solution is not to look for the planet directly, but to watch how the star's light changes as the planet orbits. Every transit, every eclipse, every phase shift leaves a trace in the starlight, a modulation so small that it can only be detected with extraordinary precision. These traces, combined and repeated, create a fingerprint that reveals the hidden companion. Phase curves are one of the most powerful of these tools. As the planet circles its star, the fraction of its illuminated side facing Earth changes, just as our moon waxes and wanes. The total brightness of the star plus planet system rises and falls in rhythm with the orbit. For a bright planet, this curve is pronounced. For a dark planet, it is almost flat, but even the smallest variations can be measured if the instrument is steady enough. By analyzing these curves, astronomers not only detect the presence of a planet, but also deduce its albedo, its heat distribution, and even hints of its weather. Secondary eclipses provide another avenue. When the planet slips behind the star, any contribution it makes to the system's brightness disappears temporarily. By measuring the difference between the combined light and the starlight alone, astronomers isolate the planet's signal. This method is especially valuable for planets like TRES 2b, whose visible reflection is nearly absent, but whose infrared emission is significant. The tiny dip in brightness during an eclipse, sometimes only a few parts per million, becomes the key to unlocking the properties of an entire world. The instruments that make such measurements possible are marvels of engineering. The Kepler spacecraft was designed to monitor the brightness of stars with an accuracy better than 1 part in 10,000. Its detectors were shielded from temperature fluctuations, its orientation maintained with gyroscopic precision, its data pipeline refined to filter noise without erasing signal. The result was a stability that ground-based telescopes could not match, allowing the discovery of thousands of planets, including the darkest of them. Spitzer, though optimized for infrared, added complementary power, revealing the heat that dark planets re-radiate. Together, these observatories demonstrated that with enough sensitivity, even the invisible can be observed. Hubble, too, played a role, particularly in transmission spectroscopy. When a planet transits, some of the starlight filters through its atmosphere. By analyzing the spectrum of this light, astronomers detect the fingerprints of molecules. Sodium, potassium, water vapor, and other species leave subtle marks that reveal composition. For dark planets, this method is often the only way to probe their atmospheres, since reflected light offers so little. By combining transit spectroscopy with phase curves and secondary eclipses, a three-dimensional picture emerges, woven from the faintest of signals. Yet the challenges remain immense. Stars flicker with magnetic storms and pulsations, masking planetary signals. Cosmic rays strike detectors, leaving false spikes. Instruments drift with time, creating trends that must be corrected. Data reduction becomes as important as observation, requiring careful algorithms that separate astrophysical signal from instrumental artifact. Teams of scientists spend years refining these methods, ensuring that what remains is truly the voice of a planet and not the illusion of noise. The success of these techniques speaks to the philosophy of astronomy itself. Knowledge does not always require direct vision. We do not see exoplanets as disks in a telescope. We infer their presence from the way they tug on stars, dim their light, or alter the spectrum of photons. The invisible becomes visible through inference, mathematics, and persistence. TRES 2b is known not because it shines, but because it fails to shine, and because we have learned how to interpret that failure. The pursuit of the invisible continues to drive innovation. New detectors are being designed with even lower noise floors. Spacecraft are being built to block the light of stars with coronagraphs and star shades, creating artificial eclipses that reveal the faint planets beside them. Interferometry, which combines light from multiple telescopes, promises to sharpen resolution and separate starlight from planetary light more effectively. Each advance brings the dream of direct imaging closer, a day when even a dark planet like TRES 2b might be seen not as a curve or a dip, but as a point of light in its own right. For now, the triumph is that we can measure the darkness of planets at all. To record the absence of reflection across hundreds of light years is a feat that speaks to both the power of technology and the patience of science. Observing the invisible is not a contradiction. It is the essence of exoplanet astronomy. It shows us that light, even when absent, still carries a message, and that by listening closely enough, we can hear the whispers of worlds that refuse to shine. Spitzer's contribution to the study of invisible planets cannot be overstated. While Kepler excelled at detecting transits and measuring albedo in visible light, Spitzer worked in the infrared, the domain of heat. This proved essential for understanding planets like TRES 2b, which reflected almost no visible light but radiated intensely in infrared due to its searing temperatures. By recording the faint thermal glow of these worlds, Spitzer confirmed that they were not simply dark shadows, but dynamic systems in energy balance, absorbing starlight and re-radiating it as heat. The contrast between invisible reflection and visible emission was one of the great insights of exoplanet science in the early 21st century. Infrared observations also opened the door to studying atmospheric circulation. On a tidally locked planet, where one hemisphere faces eternal day and the other eternal night, heat distribution is a defining property. Spitzer's phase curve measurements revealed how much heat was retained on the day side and how much was transported to the night side by winds. For some planets, night sides were surprisingly warm, suggesting efficient circulation. For others, night sides were much cooler, indicating that heat was trapped on the star-facing hemisphere. In both cases, the data spoke of weather systems beyond imagination, winds racing at thousands of kilometers per hour, and jet streams circling entire planets. TRES 2b itself showed a clear dayside glow, confirming its extreme heat, but also left open questions about how evenly that heat was spread. Hubble extended this work with transmission spectroscopy, capturing the signatures of sodium, potassium, and water vapor in planetary atmospheres. For dark planets, these signatures helped explain why reflection was absent. Where sodium and potassium dominated, their strong absorption features swallowed photons before they could escape. Where high-altitude hazes appeared, they absorbed rather than scattered, deepening the darkness. By combining Hubble's spectra with Spitzer's infrared curves and Kepler's visible data, astronomers began to piece together comprehensive portraits of planets that would otherwise be lost in the glare of their stars. Still, the instruments of that era were limited. Kepler was optimized for detection, not characterization. Hubble and Spitzer, though powerful, were designed for broader astrophysics, not exoplanets alone. Their results were groundbreaking but incomplete, tantalizing rather than definitive. Astronomers dreamed of a new generation of observatories designed specifically for the study of planetary atmospheres. Those dreams materialized with the James Webb Space Telescope. James Webb carries instruments capable of measuring spectra across a wide range of infrared wavelengths with extraordinary precision. For planets like TRES 2b, it offers the chance to go beyond brightness curves and measure the actual fingerprints of atmospheric molecules. Webb can distinguish between sodium and potassium, between titanium oxide and vanadium oxide, between hazes and clouds. It can measure thermal emission across both day and night sides, mapping circulation in detail. For the first time, astronomers can probe the chemistry of ultra-dark planets, not by inference, but by direct spectral analysis. Early results from Webb have already begun to reveal complex atmospheres, with signatures of water vapor, carbon dioxide, and exotic molecules. In the coming years, Webb will likely refine or even redefine our understanding of why some worlds shine while others vanish into darkness. Beyond Webb lies Ariel, a mission dedicated to surveying hundreds of exoplanet atmospheres. Unlike Kepler, which focused on detection, or Hubble, which balanced multiple disciplines, Ariel is designed with a single goal: to measure composition, temperature, and albedo across a statistically significant sample of planets. Its strength will not be in the depth of individual observations, but in breadth, creating a comparative framework that shows how albedo varies with temperature, mass, and stellar environment. In that data, the uniqueness of TRES 2b will be tested. Is it truly an outlier, or one of many worlds that reflect almost nothing? Ariel promises the answer. Ground-based observatories are also preparing to play their part. The extremely large telescope in Chile, with a mirror spanning 39 meters, will provide sensitivity and resolution beyond anything built before. Adaptive optics will sharpen its vision, allowing it to tease out planetary signals from stellar glare. Combined with space-based observatories, it will extend phase curve studies and eclipse measurements to planets fainter and smaller than ever before. For the study of planetary darkness, this means moving beyond hot Jupiters into the realm of smaller, cooler worlds, testing whether low albedo is confined to extremes or spread more widely across the galaxy. The synergy between instruments is where the future lies. Kepler revealed the population, Spitzer mapped the heat, Hubble traced the chemistry, and Webb and Ariel promised to unite these threads into a coherent story. Together they form a bridge from detection to understanding, from observing dips in brightness to probing the inner workings of alien atmospheres. Observing the invisible has moved from proof of concept to a robust science, capable of explaining why planets differ so radically in their relationship with light. Yet even as these tools advance, the central truth remains humbling. We are studying worlds we cannot see directly, worlds that appear only as faint perturbations in starlight. Every conclusion is drawn from photons that have traveled across light years, filtered through instruments, processed by algorithms, and interpreted by theory. The fact that such a chain can yield precise knowledge of reflectivity and chemistry is one of the triumphs of modern science. It is a reminder that invisibility is not the same as unknowability. With enough patience and precision, even the darkest worlds can be brought into view. The frontier of observing the invisible stretches beyond even the achievements of Kepler, Hubble, and Spitzer. Astronomers are now designing instruments that aim not just to infer planets from the behavior of starlight, but to separate their faint glow directly from the overwhelming glare of their stars. The challenge is immense. To see a planet beside a star requires suppressing the star's light by factors of billions, like spotting a firefly circling a lighthouse from across an ocean. But the rewards would be transformative, allowing us to study even the darkest worlds as distinct points of light in their own right. One of the most promising techniques is the coronagraph. Originally developed for solar astronomy to block the blinding disk of the sun and reveal its faint corona, coronagraphs have been adapted for exoplanet studies. Inside a telescope, a small mask blocks the light of the star, while allowing light from nearby companions to pass through. Advanced optics then suppress the remaining glare, revealing the faint planetary signal. With coronagraphs, future space telescopes may be able to image giant exoplanets directly, even those with very low albedos. Such images would not show details like continents or clouds, but would provide a direct measure of brightness across wavelengths, free from the indirect methods of transits and eclipses. Another approach is the starshade, a separate spacecraft designed to fly thousands of kilometers away from a telescope, unfurling a giant flower-shaped screen to block starlight before it ever enters the optics. The starshade casts a deep shadow over the telescope, suppressing glare and allowing the planets beside the star to shine through. This technique, still in development, could one day enable imaging of Earth-sized planets as well as giant ones. For ultra-dark worlds like TRES 2b, a starshade would make the difference between invisibility and detection, lifting the veil of starlight that hides them. In parallel, machine learning is transforming the way data is interpreted. The signals of exoplanets are faint, often buried in noise. Traditional statistical methods can extract much, but subtle patterns sometimes remain hidden. Neural networks trained on simulated light curves are now capable of identifying transits, phase variations, and eclipse signatures that human eyes and conventional algorithms might miss. Applied to the study of low albedo planets, these tools sharpen the precision of albedo measurements and help distinguish genuine darkness from instrumental artifacts. They also allow astronomers to process the vast datasets produced by modern observatories, turning floods of photons into coherent pictures of alien skies. Direct imaging and advanced algorithms are complemented by interferometry, the technique of combining light from multiple telescopes to simulate a single giant instrument. Arrays of telescopes working in concert can achieve resolution far beyond any single mirror. Applied to exoplanets, interferometry could one day reveal the spectra of even faint, dark worlds, resolving their thermal emission and scattered light separately. The path is technically demanding, but the potential is profound. To move from indirect inference to direct characterization, even for planets that reflect almost nothing. These innovations matter because they push astronomy closer to answering fundamental questions. Why do some planets form reflective clouds, while others remain bare? How do chemistry, temperature, and circulation combine to determine whether a world gleams or vanishes? Are ultra-dark planets like TRES 2b rare extremes, or are they common outcomes of planetary evolution? The next generation of instruments is designed not only to detect but to explain, to move from catalogues of orbits to libraries of atmospheres. The philosophy of this pursuit is as striking as the technology. To study what is invisible demands a kind of faith in method, a confidence that careful measurement and inference can reveal truth where no image can yet be seen. Astronomy has always operated at this boundary. Long before exoplanets were confirmed, their existence was suspected from logic and theory. Now, their presence is known, and their properties can be measured, even when they reflect almost no light. Observing the invisible is not a contradiction. It is the very essence of astronomy, the art of reading messages carried across the void by photons, however faint. As this chapter of science advances, the discovery of TRES 2b serves as both inspiration and challenge. It reminds us that planets can defy expectation, appearing darker than coal, and that our instruments must be refined to capture such extremes. It also reminds us that invisibility is temporary. What seems unreachable today may tomorrow be measured with ease. As new telescopes rise and new techniques mature, the invisible does not remain so forever. With persistence, patience, and imagination, the universe always reveals itself. And so, the study of planetary darkness moves forward, powered by coronagraphs, star shades, interferometers, and algorithms, each designed to hear whispers against the roar of starlight. The invisible is brought into view, and in its shadows we find knowledge. The next stage will be to use these tools not only to confirm what we suspect, but to discover what we cannot yet imagine, expanding the boundaries of planetary science. Once again, the discovery of planets like TRES 2b forces us to look deeper into the processes that shape worlds. At first, a planet's albedo may seem like a superficial quality, nothing more than the brightness or dimness of its appearance. But in truth, a planet's reflectivity carries profound implications. It encodes the chemistry of the atmosphere, the history of migration, the influence of stellar radiation, and the circulation of winds that redistribute heat across hemispheres. Darkness is not trivial. It is a signal, a visible outcome of billions of years of planetary evolution. To measure it is to glimpse a world's past, as well as its present. In the classical view of planet formation, giant planets take shape in the outer regions of protoplanetary disks, far from the central star. Beyond a threshold known as the snow line, temperatures are low enough for water, methane, and ammonia to freeze into solid grains. These ices provide the building blocks for massive cores, which in turn attract huge envelopes of hydrogen and helium. This is how Jupiter and Saturn came to be: cold, cloud-laden, and reflective. But hot Jupiters like TRES 2b present a problem. They orbit so close to their stars that ices could never have condensed there. Their very existence suggests that they must have formed farther out and then migrated inward. Migration is now central to the story of hot Jupiters. Driven by gravitational interactions with the disk or with other planets, they drift across the system until halted by resonances or the dispersal of gas. Inward migration carries them into regions of extreme stellar irradiation, where their atmospheres are heated to over 1,000 degrees Celsius. In these environments, the clouds that brighten Jupiter and Saturn cannot survive. Instead, skies are stripped down to bare gases, filled with sodium and potassium that absorb visible light. What remains is a world darker than coal, a planet where migration has erased reflection. Darkness, in this sense, is the visible scar of a violent journey. Atmospheric chemistry confirms this narrative. On Earth, reflection comes from clouds of water droplets and scattering by nitrogen and oxygen. On Jupiter, ammonia crystals brighten the cloud tops, while methane adds reflective hazes. On TRES 2b, however, the temperatures are too high for such condensates to exist. Water remains vapor. Ammonia and methane are destroyed. In their place, alkali metals dominate, and their absorption lines suppress visible reflection. Models also suggest the presence of exotic molecules, such as titanium oxide and vanadium oxide, compounds that in cooler atmospheres would condense, but here remain gaseous, further darkening the sky. Albedo, in this way, becomes a fingerprint of chemistry under duress. Darkness also reflects the circulation of the atmosphere. Hot Jupiters are tidally locked, with one hemisphere facing eternal day and the other eternal night. On the night side, temperatures fall low enough for transient clouds to form. Winds racing at thousands of kilometers per hour sweep these clouds into the dayside, where they evaporate instantly in the heat. The cycle prevents a stable reflective layer from forming. Thus, the very winds that might have balanced temperature instead enforce darkness, maintaining bare, absorptive skies. Circulation, chemistry, and stellar radiation conspire together to produce a world without reflection. Evolutionary models reveal that this is not a passing condition but a stable one. Over billions of years, planets like TRES 2b remain dark because their irradiation never lessens. Unlike Jupiter, which cools slowly and retains clouds, a hot Jupiter's destiny is to absorb. Albedo values near zero are not accidents of timing, but long-term outcomes of physics. This makes TRES 2b an anchor point in planetary science, a case that shows the lower bound of reflectivity. Other planets may vary, but none yet has been found darker. This knowledge carries significance beyond hot Jupiters. The same physics that makes TRES 2b dark applies to other planets as well. On rocky worlds, albedo affects climate directly. Earth's 30% reflectivity helps regulate temperature. If our planet reflected less, it would absorb more solar energy and heat uncontrollably. If it reflected more, it would freeze into a snowball. The extremes seen on hot Jupiters teach us how delicate this balance is. By understanding why TRES 2b is black, we learn the principles that may determine habitability on smaller planets. Darkness, therefore, is not irrelevant to life. It is part of the physics that sets the stage for whether life can exist at all. Comparative planetology relies on such extremes. By studying the brightest planets alongside the darkest, astronomers map the full range of possibilities. Venus, with its brilliant sulfuric acid clouds, reflects 75% of sunlight. TRES 2b reflects less than 1%. Between these extremes lies a continuum, each point shaped by a combination of chemistry, temperature, and radiation. The richness of this continuum demonstrates that planets are not variations on familiar themes but products of diverse histories. Diversity is not noise but data, and TRES 2b is among the most valuable data points of all. Dark planets also serve as natural laboratories for physics under conditions that cannot be reproduced on Earth. Temperatures above 1,000 degrees Celsius, pressures dozens of times greater than Earth's atmosphere, and radiation levels far beyond terrestrial standards push molecular behavior into new regimes. Sodium and potassium absorb light differently under these pressures. Complex oxides may remain gaseous instead of condensing. Winds may circulate heat supersonically. By modeling these processes and comparing them to observations, scientists refine fundamental theories of chemistry and fluid dynamics. What cannot be built in a laboratory can still be studied in the skies of a distant planet. The philosophical lesson of darkness is equally profound. For centuries, brightness was equated with presence, darkness with absence. But TRES 2b reverses this. Its darkness is not emptiness, but signal, a measurable quality that encodes information. The failure to reflect light is itself data that tell us how molecules behave, how atmospheres circulate, and how migration sculpts planetary destinies. In this way, darkness becomes evidence, as rich in meaning as brightness. The planet's near invisibility is not a barrier to knowledge, but a pathway to it. Thus, the study of TRES 2b teaches us more than the properties of a single world. It shows us how planetary systems evolve, how chemistry operates under extremes, and how context shapes destiny. It demonstrates that migration, radiation, and circulation combine to create outcomes far beyond the familiar. It highlights the importance of diversity, reminding us that the solar system is only one set of examples among many, and it proves that even the darkest planets can illuminate, their silence carrying messages across light years. The darkness of TRES 2b is not an anomaly. It is part of the spectrum of planetary outcomes. By embracing it, we expand our understanding of the cosmos, moving beyond the expectation of brightness to recognize the meaning of shadow. In the end, TRES 2b is not just a dark planet. It is a teacher, showing us that every photon reflected, absorbed, or absent tells a story. And the story it tells is that the universe is more diverse, more inventive, and more surprising than we ever imagined. When astronomers announced that they had found a planet darker than coal, the reaction spread far beyond the walls of academia. Within the scientific community, the discovery of TRES 2b was at once thrilling and puzzling. By the early 2010s, exoplanets were no longer novelties. Hundreds had been confirmed, and their diversity was already reshaping ideas about planetary systems. Yet this one stood apart. Its albedo, measured at less than 1%, was so extreme that even seasoned scientists paused. Planets were expected to be bright or dim, depending on clouds, but not nearly invisible. A gas giant reflecting almost no light at all seemed improbable, even unsettling. The immediate response among astronomers was careful. The data came primarily from Kepler, whose instruments could measure tiny fluctuations in stellar brightness. Still, extraordinary claims require extraordinary verification. Teams checked and rechecked the light curves, considering whether stellar variability, instrumental drift, or data processing errors could mimic such darkness. Independent groups used different models and filtering methods, and the result held. The phase curve of TRES 2b was flat, its reflection negligible. The confidence grew that this was not illusion, but reality. Caution remained, error bars were emphasized, uncertainties carefully explained, but the excitement was unmistakable. Once the measurement was secure, attention turned to explanation. What atmospheric chemistry could erase reflection so thoroughly? Sodium and potassium were obvious candidates, their absorption lines well known. Titanium oxide and vanadium oxide offered another path, their strong absorption extending across visible wavelengths. Some speculated about hazes, not the reflective hazes of Earth or Titan, but absorptive ones, particles that swallowed photons instead of scattering them. Theories diverged, but all agreed on the central point. TRES 2b's darkness was not a violation of physics, but an extension of it. The laws were familiar, but the outcomes were new. The reaction outside academia was different in tone, but no less powerful. News outlets quickly seized on the phrase, pitch black planet. Headlines described a world blacker than coal, darker than asphalt, almost invisible against the void. These metaphors, while not strictly scientific, captured imaginations. Illustrations accompanied articles, showing a black sphere orbiting a golden star, glowing faintly red with heat. Though no telescope had yet taken such an image, the concept was enough to make people pause. A planet that swallowed starlight sounded like something from myth, yet here it was, measured and confirmed by instruments across hundreds of light years. This divergence between scientific precision and cultural metaphor was not a flaw but a dual strength. For scientists, albedo values and spectral models were the heart of the matter. For the public, comparisons to coal and velvet made the concept tangible. Each approach served its audience. The rigor of science ensured that the discovery was trustworthy. The resonance of metaphor ensured that it was memorable. Together, they propelled TRES 2b beyond the journals and into the cultural imagination, where it became a symbol of the strangeness of the universe. Within universities and classrooms, TRES 2b quickly became a teaching example. Professors contrasted its less than 1% albedo with the 30% of Earth, the 50% of Jupiter, and the 75% of Venus. The contrast was dramatic, unforgettable. Students grasped the idea that albedo was not trivial but essential, shaping climate and reflecting deeper atmospheric processes. TRES 2b's darkness made the lesson vivid. It proved that planetary science was alive, not confined to the solar system, but expanding into realms no textbook had predicted. For many outside the field, the discovery carried symbolic weight. Darkness has long been a cultural metaphor for mystery, the unknown, or even danger. To learn that the cosmos contains actual worlds of almost pure darkness stirred imaginations. Writers and artists wove it into stories, describing planets of shadow, orbiting close to fiery stars. In doing so, they blurred the line between science and metaphor, between data and meaning. Scientists, careful to preserve accuracy, often found themselves acknowledging the usefulness of metaphor as a bridge. A phrase like, "the darkest planet ever found," reached audiences who might not have been drawn in by technical charts. Outreach became not only about precision, but also about connection. The long-term scientific impact of TRES 2b was equally significant. It shifted priorities, showing that measuring albedo was not merely a side project, but a path to fundamental insight. Proposals for telescope time began to highlight reflectivity studies, seeking to determine whether other planets shared such darkness. Future missions like Ariel were designed with these questions in mind, promising systematic surveys of planetary albedos. In this way, TRES 2b shaped not only public imagination, but also scientific agendas, reminding agencies and researchers that even surprising results demand thorough exploration. The legacy of the discovery also highlighted the role of extremes in science communication. People are drawn to boundaries: the hottest, the coldest, the largest, the smallest. TRES 2b fit neatly into this pattern, becoming the darkest. By marking an edge of possibility, it gained a status greater than the sum of its measurements. It showed that even something as abstract as albedo could become a cultural touchstone if presented in the language of extremes. Darkness, in this case, was not absence, but presence, an extreme that defined the lower limit of planetary reflectivity. Perhaps the most lasting reaction was the recognition that TRES 2b illuminated both science and culture simultaneously. For scientists, it refined models of hot Jupiter atmospheres. For the public, it provided a symbol of mystery and wonder. For educators, it offered a vivid example. For artists, it sparked inspiration. Rarely does a single discovery bridge these domains so effectively. The darkness of TRES 2b was both evidence and metaphor, both measurement and story. In the end, the reactions to TRES 2b converged on a single truth: that the universe is more diverse than we expect. A planet can orbit a star like the Sun and yet reflect less light than coal. Such strangeness reminds us that discovery is not only about confirming theories, but about encountering the unexpected. Scientists embraced the challenge. The public embraced the wonder. Together, their responses ensured that TRES 2b would be remembered not only as a data point, but as a milestone in humanity's exploration of the cosmos. The story of TRES 2b does not end with its discovery. In science, no single result is ever the final word. Each measurement becomes a stepping stone, guiding the path toward deeper questions and sharper tools. The darkness of this planet is not just a curiosity, but a challenge, one that has already shaped the way astronomers design missions, frame priorities, and imagine the next era of exploration. To look forward is to recognize that TRES 2b is part of a continuum, a reminder that the universe always has more surprises in store. The James Webb Space Telescope represents the first great leap into this new era. With its extraordinary sensitivity to infrared light, Webb has already begun mapping the thermal emission of exoplanets. For dark worlds, this is critical. They may reflect almost nothing in visible light, but they re-radiate enormous amounts of energy as heat. Webb can measure not only the brightness of this emission, but also its distribution across different wavelengths, revealing the molecules responsible for absorption. For TRES 2b, this means that the flat phase curves of Kepler will be supplemented by detailed spectra, pointing to the precise chemistry that erases reflection. Sodium and potassium may be confirmed, or titanium oxide and vanadium oxide may play larger roles than expected. What was once inferred will soon be measured directly. Webb also offers the possibility of mapping temperature across hemispheres. On tidally locked hot Jupiters, the question of how heat flows from dayside to nightside is fundamental. Some planets show strong circulation, smoothing out temperature differences. Others remain sharply divided, with blistering daysides and cooler nightsides. For TRES 2b, such mapping could reveal whether its darkness is uniform or patchy, whether transient clouds form on the night side before evaporating in daylight. By connecting circulation to albedo, scientists will understand not just why the planet is dark, but how that darkness is maintained over time. Beyond Webb, the European Space Agency's Ariel mission promises to shift the study of albedo from case studies to populations. Scheduled for the late 2020s, Ariel will survey hundreds of exoplanet atmospheres systematically. Instead of a handful of extreme examples, astronomers will have a statistical library spanning a wide range of stellar types, orbital distances, and planetary masses. Within this library, the place of TRES 2b will be clearer. Is it the darkest of a rare few, or one of many near-black worlds? Does its albedo represent an outlier or a natural end of a spectrum? Only a broad survey can answer such questions, and Ariel is designed for exactly this task. On Earth, the coming generation of giant telescopes will complement this work. The extremely large telescope in Chile, with a primary mirror nearly 40 meters across, will bring unprecedented resolution and sensitivity to ground-based astronomy. With advanced adaptive optics, it will separate planetary signals from starlight more cleanly than ever before. For dark planets, this may allow direct detection of faint reflections that space telescopes miss. Combined with Webb and Ariel, these ground-based giants will ensure that darkness is studied across multiple platforms, each strengthening the conclusions of the others. Looking even further, concepts like coronagraphs and starshades promise to transform the field. Coronagraphs, already being tested on upcoming space telescopes, block a star's light inside the instrument itself, revealing the faint companions nearby. Starshades, still in development, would fly tens of thousands of kilometers from a telescope, casting a deep shadow that suppresses starlight before it even enters the optics. These methods could one day allow direct imaging of exoplanets, including those as dark as TRES 2b. While such planets will remain faint, the ability to isolate their light would allow detailed spectra and precise albedo measurements. Darkness would no longer be inferred, but directly observed. Computation will play a growing role as well. Machine learning algorithms are already proving their worth in identifying subtle transit signals and phase curve variations. As datasets expand into terabytes and petabytes, these algorithms will become essential for extracting faint planetary signatures from noise. For albedo studies, they may reveal weak patterns missed by traditional analysis, distinguishing between absorption by molecules, scattering by particles, and instrumental artifacts. In this way, artificial intelligence becomes a partner in discovery, turning streams of photons into coherent stories of planetary behavior. The search for darker worlds than TRES 2b is ongoing. It is entirely possible that new instruments will reveal planets with albedos so low that reflection is indistinguishable from zero. Such worlds would test the limits of chemistry and radiation, forcing models to explain how atmospheres can be stripped of every reflective particle. At the same time, brighter planets will also be found, gleaming with reflective clouds of silicates or metal oxides. Each extreme is valuable, each data point filling in the mosaic of planetary diversity. TRES 2b may remain the darkest known for years, but eventually it will be joined, perhaps even surpassed, as the catalogue of worlds grows. The implications of these discoveries extend beyond hot Jupiters. The same physics governs the climates of smaller planets, including those in habitable zones. Albedo determines how much light a planet absorbs, which in turn sets its surface temperature. On Earth, this balance keeps oceans liquid. A small change in albedo can tip the planet into ice ages or warm periods. By studying extremes like TRES 2b, scientists refine the physics that will one day be applied to Earth-sized exoplanets, helping to determine which are truly capable of supporting life. Darkness, though inhospitable in this case, informs the search for habitability elsewhere. Culturally, future discoveries will continue to capture imaginations. Just as TRES 2b became known as the pitch-black planet, new worlds will be framed in metaphors. Planets brighter than Venus, planets glowing crimson with heat, planets colder than Pluto. These descriptions will not diminish the science but amplify it, carrying discoveries beyond academia into classrooms, media, and art. Darkness will remain a potent image, but it will be joined by brightness, color, and contrast, expanding the palette of what planets can be in the human imagination. In the end, looking forward means acknowledging both how far we have come and how far we have yet to go. A generation ago, no exoplanets were known. Today, thousands are catalogued, and some, like TRES 2b, are characterized in detail. The next generation will not only add to these numbers but deepen our understanding, turning statistics into stories of formation, migration, chemistry, and climate. The darkest planet ever found will no longer stand alone, but will be one of many examples, each revealing how the laws of physics play out under different conditions. And yet TRES 2b will remain significant, not only as the first planet of near-total darkness, but as a reminder of what discovery means. It shows that even the absence of light can be evidence, that invisibility is not the same as unknowability. It shows that science thrives on surprises, that every unexpected measurement is an opportunity to learn. And it shows that the cosmos is not arranged for human eyes, but for its own purposes, indifferent yet legible to those who learn how to read it. As this book closes, we leave TRES 2b not as a solitary marvel, but as part of a larger journey. It stands as a milestone in the exploration of exoplanets, a symbol of the diversity that awaits us, and a challenge to push instruments and theories further. Its darkness, far from being an obstacle, has illuminated the path forward. The next generation of discoveries will follow that path, revealing new worlds brighter, darker, stranger, and more profound. The universe is not finished, surprising us, and perhaps it never will be.